Ashok sir.
Start చేయండి మేడం.
నెక్స్ట్ స్పీకర్ సార్ కి నేను మరి మెయిల్ పెట్టాను, వాట్సాప్ కూడా పెట్టినా, నోటెడ్ పెట్టినారు ఆయన. మేబీ హిల్ జాయిన్ ఆన్ టైం. మీరు ఒకసారి
నేను 10-15 minutes ముందు కాంటాక్ట్ చేస్తాను.
జస్ట్ కాంటాక్ట్ లో
స్టార్ట్ చేయండి మేడం.
సార్ shall I start?
Yes sir, yes.
Okay sir. Good afternoon, everyone. Are you able to hear me?
Yes, madam. Yes.
Okay, sir. Thank you. So, good afternoon, everyone. Myself, Professor Leelavati from Department of Chemistry, Osmania University, the sectional president of this ICC 40th conference. So my topic, I'm going to talk on the topic already I've given. I'm going to talk on synthesis of newer.
Madam, Vasudev Reddy గారిని introduce చేయండి.
Mami start చేయమన్నారు కదా, నేను అందుకని I thought of going ahead.
Just invite.
Sir.
I am ready with your introduction, madam.
Okay. Sir, brief, sir.
Very brief.
Already I have given brief, sir.
Shall I start, sir?
Sir, yes, sir.
Good afternoon, one and all. Good afternoon, my teachers who are in virtual meeting. It is my pleasure to invite Professor Leelavati Madam to deliver a talk on synthesis of newer fused quinoline heterocycles of biological interest. She is the president of this section. Professor Leelavati Madam completed her PhD from ICT in 1993. Later, she joined in Osmania University. Madam published several publications in reputed journals and completed 2 research projects. She is well-known academician, also administrator. She is now working as chairperson BOS, and before that she worked as several positions. Now I invite Madam with this brief introduction to deliver the talk on the quinoline heterocycles.
Thank you, sir. Thank you, sir. Once again, good afternoon, everyone. Thank you, Vasudev Reddy, sir, for introducing me to the audience. And so just now I mentioned my talk is on synthesis of fused quinoline heterocycles, which are of biological interest. So everyone, they are familiar with the heterocycle. So the moment we hear the name quinoline, the quinine comes to our mind. Just now you heard about strychnine in Chandrasekhar's presentation. So quinine also belongs to the class of alkaloids. And all of you are aware that it is an anti-malarial drug. And then later, the synthetic drug developed, the other common synthetic drug developed for malaria is chloroquine. This also you can see the presence of quinoline nucleus. And a few others I've just given on this slide where you can see the importance of the quinoline derivative. So here, this is once again malarial, used in the malarial treatment. Then the other one you can see this is an anti-cancer drug. So such is the importance of the quinoline derivative. So by looking at the importance of the quinoline, one can say that That is the beauty of this. Not only quinoline, most of the organic molecules, we know they are used as a drug, but especially why we focused on the synthesis of quinoline derivatives is for two reasons. One is because of their biological activity, just now I mentioned. The second reason is accessibility of the precursors in the lab very easily. So we can, our starting material, we used 2-chloro-quinoline 3-carbaldehyde, which can be easily accessed in the laboratory. And the second is because of the biological activities. So we focused on synthesis of quinoline derivatives. So this is same thing. Just now I mentioned about the importance of the quinoline in various biological activities of the quinolines. So because of that, we thought it is interesting to develop fused quinoline derivatives, which are of biological use, medicinal use. So we developed the methodologies for the construction of 3 different fused quinoline heterocycles, which I've mentioned here. The one you can see here, the quinoline that is fused to triazoloazepine or oxipine system. This is the one we have synthesized. The second one is we can see naphthyridine derivatives, where quinoline is fused to pyridine derivative. So the heterocycle what we have synthesized is naphthyridines. And the third one is where quinoline is fused to furan, that is benzopherophenolines. So 3 different heterocycles. So my presentation is concentrated on the construction of these 3 heterocycles, that is benzopheroquinolines, naphthyridines, and then quinoline fused triazoloazepines and oxipines. So then in this 15 or 20 minutes, I'm going to focus on these synthesis of these heterocycles. And I'm beginning with the synthesis of benzopheroquinolines. I'm beginning with the synthesis of benzopheroquinolines. So we have synthesized this benzopheroquinolines starting from, just now I said that the precursor for the synthesis is chloroquinoline 3-carbaldehyde, which is converted into this carboxylic acid derivative. And then you can see the 2 functional groups are present in this moiety. One is carboxylic acid, the other one is halogen, which is suitable for cyclization. So we subjected this to decarboxylative cross coupling in the presence of palladium acetate. That results in the formation of benzopheroquinolines. We have prepared them in very good yield and by simple method. And this work we published in Tetrahedron Letters in the year 2021. So then just if you look at the importance of the benzopheroquinolines, I have highlighted few derivatives which are of medicinal importance. For example, here A exhibits anti-inflammatory activity. B, it is found to be neuroprotective agent. And then C, it is found to be anti-TB drugs. So few of the derivatives I have mentioned where you can see quinoline is fused to furan derivative. So motivated, encouraged by these observations, we have planned to synthesize some more benzopheroquinoline derivatives. So then for that one, so just now I mentioned, we have developed an efficient methodology for the synthesis of benzopheroquinolines, starting from this quinoline substituted carboxylic acids by decarboxylative cross coupling. Now, the starting materials, the precursors which are required for this synthesis of benzopheroquinolines, they are prepared from 2-chloroquinoline 3-carbaldehyde. So just now I mentioned also, because this is the most common starting material which can easily prepared from acetanyl anhydride reaction. So that is one of the main reason why we were concentrating on these quinoline derivatives. So here, so this quinoline carbaldehyde, it is reacted with different phenols, where we know that this chlorine is can be replaced by other nucleophiles because it is present on pyridine. So it is replaced by phenoxide ions. We are getting this phenoxy substituted quinoline carbaldehydes. Yeah, it's a lot of disturbance. Yeah, participants, please unmute yourself. I request the participants to unmute. Sorry, mute yourself. Sorry. So it's okay if my voice is clear, I'll go ahead. So these starting materials, they were prepared starting by replacing chlorine with the phenoxide ions and then subjecting aldehyde to oxidation with silver nitrate, that is mild oxidation. We are getting the corresponding carboxylic acids. And these carboxylic acids, they are subjected to decarboxylative cross coupling. That is decarboxylation simultaneously, that is loss of carboxylic group, decarboxylation along with the halogen, which is referred as a decarboxylative cross coupling. So that results in the formation of bond formation and which results in benzopherophenolines. So then initially when we tried the reaction with palladium acetate and triphenyl phosphine, with potassium carbonate as a base in acetonitrile, we got the product yield at around about 56%. And we wanted to increase the efficiency of the reaction. Further, we have tried the reaction in various conditions. We have carried out the optimization process. And we found that this is the condition that yields the best yields of the product, where palladium acetate, 5 mole% we used, and same ligand triphenyl phosphine. Potassium carbonate is also same, but then solvent from acetonitrile, it is changed to DMF, and temperature, we have increased the heating temperature, reaction temperature. So within 3 hours, therefore, from the optimization studies, we concluded that this is the best reaction condition to get the maximum yield of the product. So by subjecting, so now we are interested in preparing, finding out the substrate scope for this particular reaction. So we wanted to prepare various derivatives using this methodology. So then under the optimized conditions, we subjected different substituted quinolines to the reaction, which yielded the derivatives. We have prepared around about 20 compounds with the yields also mentioned. So we have taken quinolines with various substitutions like methyl, etc., because we easily they are accessible for methyl substituted quinolines. So we focused on that. So methyl quinolines at methyl at different position that is taken. Methoxyquinoline is also tried. Here you can see one of them is methoxyquinoline. And in place of phenols, we have gone for a simple phenol, we have gone for pyridinol, we have gone for beta-naphthol. So therefore, a wide substrate scope, you can try with various phenols here. So accordingly, we got the corresponding quinoline, furoquinolines. So if it is a phenol, benzopherophenolines, etc. If it is pyridine, then the corresponding furoquinolines. So we have prepared all of them in very good yields. Next one is we wanted to extend these to sulfur thioanalogues. So then we tried similar reaction here. Instead of phenol, we have taken the bromothiophene and prepared this carboxylic acid. But unfortunately, when we subjected to the reaction under same conditions, we could not get the product. Maybe due to the presence of sulfur, maybe it is less reactive. We didn't isolate any defined product from the reaction. So therefore, we restricted ourselves to the furoquinolines. We were unable, we could not prepare this thieno-fused, that is, this is benzothienoquinolines. We could not prepare them. So next, so therefore, only this methodology, now what we have developed, that is, we could prepare only the benzopherophenolines. Next one is we focused suggesting the possible mechanism for the reaction. I said what we have prepared is by the decarboxylative cross coupling. So this the question is whether simultaneously the carboxylic group is lost with bromine so that the bond can be formed, or an alternative mechanism is whether it first undergoes decarboxylation to give the corresponding product, then followed by CH activation type. Leads to the final product formation. So what we suggested is decarboxylative cross coupling. To rule out the decarboxylation first and then the cross coupling. So we have carried out a controlled experiment to find out exactly the mechanism how the product is formed. So we have converted, we have decarboxylated this one. We have taken this carboxylic acid. when reacted with silver carbonate in acetic acid and DMSO, it underwent a decarboxylation to give this corresponding just bromophenoxyquinoline. We got this bromophenoxyquinoline. Then we subjected this one to the same conditions under which we have prepared the benzopherophenolines. So when we subjected it to the same conditions, we got the product, but the reaction is very slow, almost 12 hours. Whereas simultaneously, when we do the reaction, we got the product within 2-3 hours. So therefore, we carried out this control experiment to rule out the possibility of the decarboxylation and then the coupling reaction, CH activation type. So from this experiment, we have concluded that it is decarboxylative cross coupling, because in our case, reaction is taking place within no time, just 2 to 3 hours. So therefore, we have concluded that it is taking place simultaneously, decarboxylation followed by the coupling. So this is the mechanism we have suggested, where initially, because this is similar to mechanism, nothing special, similar to all reactions where we use palladium acetate as the catalyst, where palladium complex is formed and quinoline is assisting in the formation of the complex. Then followed by the loss of the halogen forming palladium derivative, which coordinates with the carboxylate anion, and then loss of this one, decarboxylation of this one, followed by palladium complex. And then this from this, again, the catalyst will be regenerated and liberating the product, that is benzopherophenolines. So this is the first part of our work, where we synthesized benzopherophenolines from via the decarboxylative cross coupling, starting from the suitably substituted carbox. The another advantage, in addition to the wide substrate scope, the another advantage of this particular method is because we know the carboxylic acids are once again easily accessible. They can be easily prepared from the corresponding aldehydes, or directly they are available. So therefore, that is the scope of this particular method. Now going to the next one, the next series, what we have synthesized. That is a triazoloazepine or triazolooxipine fused quinolines, which we have prepared once again from the corresponding click derivatives. So here, these are the click derivatives we have prepared, again starting from same 2-chloro-3-formyl quinolines, and these click compounds are subjected to CH activation. Once again, the catalyst is same palladium acetate. So then this is via the CH activation, we could able to prepare that is triazolooxipine fused quinolines and then triazoloazepine fused quinolines. So 2 series of compounds we have prepared, and this work we published in RSC journal, that is New Journal of Chemistry. So then this is just a few examples I've cited here to see the importance of these oxipines and azepines. So you all know triazoles, the importance of the triazoles. Here it contains 3 important pharmacophores in this molecules, and this is so far this quinoline fused triazolooxipines and azepines are not reported. So we are the first one to report this cyclic system. In this, you can find 3 pharmacophores. One is the quinoline system, the other one is azepine or oxipine, the other one is the triazole. Each is important in its own way. Quinoline is in the beginning of the presentation itself, I mentioned the importance of the quinoline. Oxipine is another heterocycle, which we, when it is specially fused to benzene and etc., other heterocycles, it exhibits various biological activities. And triazole, we all are familiar. Once again, triazole, that is the easily that can be prepared in the laboratory, and then its stability, easy preparation, stability, combined with applications. So now mostly many of the triazole containing drugs are also there in the market. So then few of the examples I have given here. We can see this is the azepine, where benzofused azepines, they are the antidepressants. And here we can see azepine fused with triazole, which is used as a AIDS, anti-AIDS, which is a HIV protease inhibitor. And here once again oxipine, that is antifungal. And this is quinoline fused triazole, which is used as a bronchodilator. So this is the importance of these heterocyclic systems, be it a azepine or a triazole or this is the quinoline. So therefore we designed the synthesis. So our planning is, the synthetic planning is, this is we planned that, so we are interested in, because our starting material is this one, we wanted to construct this heterocyclic system. So therefore we designed the synthesis in this way. So we thought that this can be easily prepared via the CH activation from the corresponding quinolones. So therefore the corresponding triazoles, and these triazoles easily can be obtained from the click reaction from the corresponding propagyl derivatives. And this propagyl can be obtained by the propagylation of the corresponding alcohols or imines. These alcohols or imines in turn can be obtained from the quinoline aldehyde by reduction or reductive amination. So this is our strategy, the synthetic planning for the synthesis of this particular heterocycle. So then the precursors, once again, these precursors, they are the imines or alcohols and propagyl derivatives and the click products. They are prepared starting from the quinoline aldehyde. So this quinoline aldehyde by reductive amination or simple reduction. If it is reduced, you are going to get the corresponding alcohols, or reductive amination, we are going to get the corresponding secondary amines. And these alcohols or amines are subjected to propagylation. So propagylation, that is with the propagyl bromide, common N-alkylation or O-alkylation is involved, which is done in DMF and K2CO3. Only in the case of alcohols, because they are little bit less reactive, where we alkylated under phase transfer catalysis conditions, whereas for amines, just under with potassium carbonate and DMF, we could get the propagyl derivatives. Now these propagyl derivatives are subjected to click reactions with various azides, which yielded the triazole derivatives. Now these are our precursors for the preparation of the that is the quinoline fused triazole oxybins and azepines, which we are prepared from the quinoline aldehyde. Now they are subjected to CH activation. So here it is the, initially we tried this with amines, a reductive amination. The amine is taken, propagulated, subjected to click reaction, and these click products are subjected to CH activation in the presence of palladium acetate, triphenyl paspine. So initially we tried the reaction, palladium acetate, triphenyl paspine and potassium carbonate as the base. So then we could get 73%, and further when we tried the different variations, we found that in cesium, compared to potassium carbonate, in cesium carbonate, the yields were better. So we got the product in 86% yield. So therefore, this was our best reaction condition to prepare this triazole azepine fused quinolines. So this was, and by under these optimized conditions, we extended the reaction to the preparation of these derivatives. So about 17 to 18 derivatives we have prepared. Then here also you can see the change of substituents. Derivatives we can prepare by changing the three moieties. We have access to quinoline substitution, quinoline with methyl substituted quinolines and methoxy substituted quinolines. And here we can go for different benzylamines like benzylamine, methoxy benzylamines, even parafluoro, but here we didn't try parafluoro. We just tried benzyl and methoxy with this one. Aniline is a little bit less reactive, so therefore we focused only on benzylamines here. Alkylation becomes less reactive if we are going for the aniline, so therefore we focused only on benzylamines. And then other third variation possible is azides. So you can go for various azides. A number of azides can be taken here as the third variation. So therefore, three positions are there for the variation, this structure. One is in quinoline, the other one is in the benzylamine part, the other one is in the triazole part. So by varying these three, we could prepare all these derivatives in a very good yields. These are prepared. Now, once we prepared this, later we wanted to extend this methodology to the corresponding oxybins. So initially we prepared azepines. Now we wanted to extend this to oxybins. So for oxybins, we thought of going for the corresponding, instead of subjecting it to reductive amination, if we start with reduction, we are going to get the corresponding alcohol. Now those alcohols are subjected to propagylation. So that is, so that just now I mentioned alcohols are propagulated under PTC conditions to give the corresponding O propagyl derivatives, and O propagyl derivatives are subjected to click reaction. So we are getting the corresponding click derivatives, and when they are subjected to activation under the same optimized conditions, and this reaction, I think we heated about almost 36 hours. 24 to 36 hours heating, because it is CH activation. It took very long time to yield the product, but the reaction is clean. We got almost exclusively one product. This is so therefore these are the corresponding O click derivatives, that is oxygen substituted click derivatives, which on cyclization yielded the corresponding quinoline, that is triazolo-oxipene fused quinolines. So these are the again different oxipenes we have prepared using this methodology. So that's what I said. This work is published in New Journal of Chemistry. This actually we prepared this in a stepwise manner. So we attempted even one part reaction also, whether we can do click reaction and CH activation in one step. Like by going through the Ackermann literature and others, etc. We attempted, but then we were unsuccessful in getting this reaction in one part. So therefore, we have to go for the two-step reaction, that is preparing the click product and then followed by the CH activation. In two different steps we tried. And published also this work. So this is about the second series, what we have prepared, second series. Now going for the third one. The third series, what we have prepared is naphthyridine derivatives, where quinoline is fused to the pyridine component. This naphthyridine derivatives we have prepared in a sequential one part. This we have prepared in sequential one part, once again starting from this quinoline substituted secondary amines, which are subjected to N-allylation in the presence of DMF and potassium carbonate. Here in sequential one part, we did it under cesium carbonate. So then in the same reaction, we have added, after confirming by TLC the formation of N-allylated derivative, we have added the palladium acetate and then the triphenyl phosphine as a ligand, and continued with the cesium carbonate, but heated. This is at room temperature, first reaction, second reaction is heating. So in the same reaction part, we have added this and continued, and we could get the product. And this work we published in Tetrahedron Letters. So then just to see the importance of the naphthyridine derivatives, I've given few examples here, where you can see these different naphthyridine derivatives. They are associated with important biological activities. So based on this, this is the synthetic planning. So this is just, I mentioned what is this, in this part I'm going to describe it. So based on this importance of the naphthyridines, we thought of synthesizing these quinoline fused pyridines. For this, our synthetic planning is, so we thought that this could be prepared from the intramolecular Heck reaction. From Heck reaction, this target compound can be prepared. So the precursor which is required for the Heck reaction in turn can be prepared from N-allylation of this secondary amine. And this secondary amine, once again, just now we have gone through in oxipenes preparation also, that is obtained from the quinoline carbaldehyde by the reductive amination. So that is the synthetic strategy for the preparation of these naphthyridines. So therefore, initially we have prepared, we have taken this aldehyde. And then subjected to a reductive amination with different benzyl amines. We got this quinoline substituted secondary amines. They are subjected to N-allylation with allyl bromide, just with K2CO3 and DMF. So with K2CO3 and DMF allylation, we got the corresponding N-allyl derivatives. Now these N-allyl derivatives are subjected to intramolecular Heck reaction in the presence of palladium acetate. So by intramolecular Heck reaction, we obtained these naphthyridine derivatives. That is via the 6-exotrig cyclization we got it. There is another possibility. The cyclization can take place at this end also. Then that involves 7-endotrig cyclization. But this is not at all absurd. Maybe because of this, due to the difference in the stability of the rings, 6-membered is more easily preferred. So we could get only, not even traces, we isolated the other possible product. So we got only this particular product. So then once we got this product, then next we thought here, the alkylation is, the conditions for the alkylation is potassium carbonate and DMF. The conditions for the Heck reactions also we have used DMF and potassium carbonate. Actually, initially potassium carbonate, but with optimization, we went for cesium carbonate because that yielded little more yields. But initial reaction, we attempted in potassium carbonate and DMF both. So we thought that because both the reactions involve the same solvent and base, so then we thought, why not we attempt a sequential one-part type. So therefore, because you know the importance of sequential one-part or one-part synthesis, they are environment friendly, and then they are step economy. So therefore, we tried next is the sequential one-part, and we succeeded in that. Whereas we could not succeed in the case of furoquinolines and oxipins. There also we tried in both the cases, but we could not succeed there. But here that was easy. Our job was easy. Easily we could get this one in a one-part sequential reaction. So what we did is just now beginning also I described these secondary amines were annihilated. Then because cesium carbonate we took it because reaction was found to be more efficient in cesium carbonate compared to potassium carbonate. So first we were annihilated, confirmed from TLC the disappearance of this one. And once we confirmed the product, then next we added the palladium catalyst and other reagents required, and then heated for 2 hours, and we could isolate the product. So therefore, next is, so we went for this sequential one-part synthesis. By following the sequential one-part, we could prepare about 20 to 22 compounds in good yields, all the naphthalidines. And here, the substrate scope is one, you can vary this benzylamine. The other one is you can go for different substrates in the phenyl ring. So again, methyl and methoxyphenolines are taken, and here methoxy, benzyl, simple benzylamine, fluorobenzylamine, and there is no difference in the yields. Almost yields are maintained in all the cases. No significant effect of these substances on the efficiency of the reaction. So methoxybenzylamines, fluorobenzylamines are also taken. And not only this, we tried the reaction with aniline also. Aniline, toluidine and anicidine, reductive amination with aniline, toluidine and anicidine. But here the up to reductive amination it is okay, but then N-allylation is taking little bit of time compared to the benzylamines, naturally, because the electron density is taken away by aniline, so allylation is taking little bit slow. And moreover, final product also we could get only very less in the case of aniline, but that is overcome when we have taken a methoxy and a methyl anilines. That's what we noticed, mentioned. Maybe releasing groups, they are favoring this annihilation because we have tried in sequential one part. So that is affecting the reaction outcome. So finally, so that is our analysis. And then once we have prepared, we wanted to extend this methodology. See here, we changed the substance on quinoline and then benzyl moiety. Here also we wanted to try the allyl component also we wanted to change and try whether the reaction proceeds or not. For that, we tried with cinnamyl. We have for that one we have tried with cinnamyl by taking cinnamyl bromide, crotyl bromides, dimethyl allyl bromide. By taking varying all these components, we tried the reaction. So in place of allyl bromide, we have taken cinnamyl bromide. So with cinnamyl bromide, we got the product. With cinnamyl bromides, we could get these 4 products we have prepared with the cinnamyl bromide. So this component also we changed it, we could prepare 4 bromides. And then with crotyl and dimethyl allyl also we got it. But only thing is with crotyl little bit less yield, we got the product. So therefore we have loaded catalyst another 5 mole%, because other reactions are 5 mole. For this we used 10 mole%, and then heating also prolonged, then we could get some amount of product. So with cinnamyl, okay, it proceeded well, but with crotyl and dimethyl halide, the reaction is a little bit slow, but we could get the product in lesser yields, and then we characterized these products accordingly. So then that is, so finally we extended this methodology even to that one. Then we wanted to extend even to the acryl oil chloride, whether it works or not. So first started with allyl, then cinnamyl, crotyl, dimethyl halide. Then finally we tried with acryl chloride. But to our disappointment, we could not get the product. We could not get the product, this one. So this is not proceeded at all. So therefore, we thought, why don't we try in, because this initially we tried in sequential one part only with this acryl oil chloride. We could not get the product. Then we thought whether we can get this product in a stepwise manner instead of sequential, so when we tried the sequential, the N-allylation itself, we didn't get the product N-allylated only. Maybe the quinoline ring, because it is a basic, and this is acid chloride, it is interfering. So we could not get even the N-acryl derivative. So therefore, that is our result in the case of when we used this one. Then we tried, this is actually we tried because when we sent this paper for the publication, the referee wants me to try this particular reaction with this one. Of course, this we are not going to get the same analog. We are going to get a higher homolog, but with this we did not get it. We did not get the final product when we tried with this one also. And when we did again this one stepwise, we could get corresponding N-alkylated product, but that did not yielded the final product. So therefore, in these two cases, we did not get the product, but whereas in other cases, we could get the product. So this is what exactly I wanted to communicate in this presentation, where we focused on the preparation of quinoline fused derivatives. So I've concentrated on the preparation of these three series of compounds. First one is benzopherophenolines. The second one is triazole azepine or oxipine fused quinolines, and third one is the 1,6-naphthyridine derivatives. So this is my presentation, and I just wanted to thank the organizing committee of ICC for giving me this opportunity to share my work with you all. So thank you. And I special thanks to Ashok sir also, because of him, I involved in this entire process and work. So thank you once again.
Thank you, madam, for your full lecture on synthesis of different heterocyclic compounds by using new synthetic strategies, particularly through CH activation. Thank you, madam. Thank you on behalf of ICC. And
thank you, sir.
Behalf of me, sir. Sir, Ashok sir.
Next, you invite the next speaker.
He is ready,
Professor.
sir?
Sir, yeah, he has come.
Okay, sir.
He is already there. You introduce him.
Okay. Now I am going to introduce a eminent international renowned Professor Srikanth Junalagada from South Africa in this ICC conference. I feel great honor to introduce such eminent scientist. One minute. Eminent scientist Srikanth Junalagada from KwaZulu-Natal University, South Africa. He has done tremendous research in different fields like green chemistry, heterogeneous catalysis, value-added conversions and water chemistry, and particularly on nanochemistry. We all know these nanoparticles, nanochemistry is a breakthrough to entire world from last 2 decades. Sir, we are very happy to see you on this occasion, sir. I invite you to deliver the lectures. Ashok sir, unmute, mute lo.
Professor Srikant sir. Professor Srikant sir, please unmute.
Sorry for that. Okay.
Yes, yes. Yes, sir. You can share your screen, sir.
Okay. Can I start? Can I start it?
Yes, sir. Yeah.
Yes, sir.
But it's not allowing me to open, you know. Host disabled participant screen sharing, you know, you have to allow me to open my.
Sir, screen share sir. Ashok sir.
Okay, just okay, okay, sir.
No, it's not allowing me to open the screen, you know. It says host disabled participant screen sharing. That means you have to activate that screen. Can you see the screen? Hello? Can you see the screen?
1 minute, sir. 1 minute. One minute, sir. 1 minute.
Okay, no problem.
Sir, now you can do it, sir.
Okay.
Sir, are you able to?
Sir, now you can share.
Okay.
Sir, I think now you can share it.
Can you see now?
No, sir.
No, sir.
Okay. One second, just I'm trying to organize myself.
Yes, sir. Yes, sir.
I'm opening it up.
Yes.
Okay.
Okay,
Is it
sir.
okay?
Okay.
Can you see my screen? Okay.
Yes, sir.
Good morning, everybody. I'm Srikant Jonalagada from South Africa. Greetings to you all. Today, I'm going to talk about the nanocomposites and mixed oxides as renewable catalysts for the organic synthesis, focus much on the multi-component systems. And when it comes to nanotechnology, nanotechnology is a very useful technology, and now it is, these days, if you want to get any funding anywhere from, naturally, you have to use the word nano and also green. Green chemistry and nanotechnology are two buzzwords, to get the monies. And now if you look at the nano, just for us to get a feel about what is nano, I will start there, like normally when you see this sunbeam coming, you are sitting in your house, you see a sunbeam coming out, you see these small particles moving in the Brownian movement, that particles, you can see with your naked eye, those particles are roughly of 40 micron size. 40 micron size is, normally you can see the smallest particles, Now, why you can see the 40 micron particle is, those particles are not that much affected by gravity. They can float in the air. Once they are larger than 40 microns, most of the times, they settle down very quickly on the ground. And now compared to that one, you can see the 40 microns is, somewhere you see that the bacteria, smaller size of the bacteria, are the less than 40 microns, but what we see is the viruses what affecting us are like coronavirus, these are the smaller ones, like, in the range of a corona comes in the larger size of the nanoparticles, like I don't know, about 100 nanometers and above. That is where the coronavirus is. And now coming to nanotechnology, you see nanotechnology everywhere in the, whether it is the environment sector or the food and agriculture and otherwise engineering and everything, even textiles, they use the nanotechnology to develop the fiber. Now, when it is so important, we see nanotechnology everywhere. There are also some limitations in nanotechnology. One of the things is, the way nano is very small, our body mechanisms haven't got a adequate sort of a protection from the nanoparticles. What I mean is, when you breathe nanoparticles, they very easily go through your nasal system, and then you can get infected very easily. That's why you very easily can get infected by virus. And with the nanoparticles, we have got so many problems with the inhalation of the nanoparticles, and you can have the bronchitis, asthma, and to the extent, depending on the particle nature, you can get cancer even. And there are many other problems they affect the nanoparticles. That's why, when we say about nano, at the same time, we have to be cautious about how we use the nano and how beneficially we can use without harming our own situation. That is what is important to start with the emphasis on that. And let us go to our business now, green chemistry. The green chemistry, it is taught even in our curriculum, what it tells is, green chemistry is the principles based on commitment of the chemistry to not to produce the harmful and hazardous materials or use hazardous materials, or not to use hazardous solvents, like, not to generate too much waste and all that, The green chemistry, it got its prominence, started in early 90s or late 80s, but it got its prominence, these days, green chemistry is everywhere. We try to use in every aspect of our chemistry to minimize the pollution. And two Nobel Prizes have come for the work, related to the green chemistry. And with that, green chemistry got a little more attention by everybody. Now, if you look at green chemistry, you see that, look here, these are the 12 basic principles of green chemistry. All the 12 principles, what we use can be to much extent achieved by the catalysis. The reason is, there's one of the reasons, most of the industrial processes which are useful, they are catalyst based, there are very few cases exceptionally without catalyst the reaction works. The reason, once you have the catalyst, you have the additional benefits. That's why we do, normally one of the green processes, even before we think about the Haber-Bosch ammonia process, where hydrogen and nitrogen are mixed to get ammonia. That is one of the best green principles, where you have all the starting material converted into product. Now, coming to catalysis, as we know from the high school also, we know, catalysis is where you have it provides the alternate pathway for us, to get the alternate pathway. That means, minimize the activation energy. Instead of you having higher activation energy, the same reaction can be achieved with lower activation energy. That means, you can get a efficiency of the reaction and energy conservation. And now with that, this type of the catalyst, we know homogeneous and heterogeneous catalyst. Homogeneous and heterogeneous catalyst. Homogeneous means same phase reactions, and heterogeneous means different phase. Most of the times, catalyst is in the solid phase, and reactants may be in the liquid phase or otherwise sometimes in the gas phase. And that's quite common. And now if you look at even the enzyme reactions, enzyme reactions are considered homogeneous reactions most of the times, although enzyme molecules are quite bigger ones, but still there is homogeneous catalysis. And now, if you compare the benefits of homogeneous and heterogeneous catalysis, the homogeneous is one of the well-known and for a longer period it has been used, and one of the benefits of that is, normally these catalysts are, robust to the poisons and high selectivity. Reactions are better understood, and reactions can be achieved under milder conditions. And all that are the good things, the disadvantages, not relatively, these are difficult to separate because everything is in the same phase, and to get it out of the system is more problem. And then, with that, it is expensive. When it comes to heterogeneous catalysis, the disadvantage of heterogeneous catalysis is the benefit of heterogeneous catalysis. And homogeneous catalysis, compared to that, we can easily separate your catalyst material and you can reuse again and again. That's why most of the big industrial process, they use the heterogeneous catalyst so that they don't lose the catalyst and use it again and again. That is in a cost effectiveness. And normally they have longer life. But one of the problems is, these reactions have a relatively low sensitivity, and reactions are not well understood. Those are the two disadvantages. And now reactions are relatively slower compared to homogeneous. But if you can achieve those 3 points, like what I said is, you can improve the selectivity and make the reaction faster and improve the selectivity. And with that, you can get all the benefits of homogeneous catalysis and all the benefits of heterogeneous catalysis. That's why people focus on the heterogeneous catalysis. Now, when it comes to heterogeneous catalysis, we use various materials depending on their pore size. They are classified into microporous and mesoporous and macroporous materials. And these are sometimes, the pore size is very important when you are looking for the fine chemicals, particularly smaller molecules, to achieve the high selectivity. But these materials are also used in many times, differently as the support materials. Normally, when we choose the catalyst, whether heterogeneous catalyst or homogeneous catalyst, what are the parameters we look for? One is the higher selectivity and higher efficiency of the reaction. That means, good conversions we can achieve, and can we get that in the moderate conditions without having a harsh, high temperature or high pressure conditions? And what is the implications for the environment? And can we reuse the catalyst? These are the aspects, and if your catalyst fits all those parameters, that is a good catalyst. And now I'm going to talk about the nanocomposites and the mixed metal oxides. That means, not one metal. Instead of that, we can take the combination of that. What is that combination in which try to achieve a better performance of the catalyst. And there are many advantages of this one. Normally, we can achieve the lower energy requirement, and then, increase the selectivity. And then, as I said, heterogeneous catalyst, we need separation is easier. And let us look at why we use the mixed oxides. The reason is, if you look at the periodic table, we have got the color coding is very easy for us to follow, highly acidic material like chromium, molybdenum, like that. Those are the highly acidic. And we have got the highly basic, like alkaline metals and those things. And you have got the amphoteric materials like titanium, zirconium, hafnium, like amphoteric properties, and weakly acidic, weakly basic. That means, you have got different ones have got different properties. Why I'm saying this is, you have to think about, how the catalysts work. The catalyst, efficiency of the catalyst comes, when you have the material, it has to land on your active site selectively. And after the reaction, immediately it should vacate so that another molecule come and sit there. That means you have to have the bindings, selective binding onto the active site and departing within once the reaction is over. For that, the properties are very important, and what sort of material combination will make you that reaction to be successful. Now, important of the nanocatalyst when it comes to many of the materials are quite expensive. Those materials, instead of we using the large quantities, we take small quantity, but that one is distributed in the nano size onto the support. And once we have that, we achieve the nanoparticles properties, all the benefits of that, but without losing the particles into the system. And now if you look at the metal oxides, individual metal oxides also do the reaction, but the efficiency that goes down. Whereas when you use the multi-metal like bimetallic or trimetallic oxides, the combination, it will allow you to get higher efficiency. And I give you an example, like you have got some work to be done, you have got a job at home, imagine you have got work at home, you try to look at a plumber, electrician, but the thing, the electrician job is electrician job and plumber's job is plumber's job. What I mean is, even if you bring 5 plumbers, still you will have the problem, the perfection when it comes to electrician job. The same way 5 electricians can't do as good as the plumber. That means you need the electrician and also plumber. The same way mixed metal oxides both will have the role to play to achieve your goals. That like, here you see a small diagram there, you have the small active material is there on the surface of it, you have the reactants coming on to that and reaction that could proceed further. Now comes to green synthesis. The green synthesis is based on the green principles of green chemistry. What we achieve in this one is, high atom efficiency. That means, most of the molecules used will go into the final product, high selectivity and easily available materials. And one step, that is the multi-component reaction, no multi-step reaction. We have the reaction in one go. And, we try to look at environment-friendly materials used like the solvents, etc., and try to achieve the excellent yields and minimal waste. Those are the objectives of the green synthesis, and let us see how we achieve those ones. I'll give you some of the examples where we work. Look at this, the simple example we all know, I need not to tell you. Multi-step means, step by step, we do one step and get the material and separate that and purify that, use for the next step, and then get the final product, 2 steps or 3 steps, depending on the nature of that. But here in this case, in the multi-component reactions, we have all the materials in one pot and we add the catalyst and then we get the final product without you trying to separate the intermediate. With this one, the advantage, you will use less amount of the solvents to purify, but if your reaction is very efficient, only one single product coming, nothing else is coming, you won't need even the separation and you get the final product straight away. I will take you through some of the examples. That is what I'm trying to do today. All this work, this one is, silver on zirconia. We did significant work using zirconia as the support. Actually, zirconia itself is the active material, can be used also, as a catalyst. And in this one, although I'm showing in one screen everything, most of the times what it happens, you scan all the materials, different catalysts, different metal oxides has their efficiency and different support materials, their activity, and then we try to combine the different ratio that of the active material and the support. Like in this case, at the bottom, you can see the 3 diagrams, 1% silver on zirconia, 2.5% zirconia, and 5% zirconia. And on this, I want to spend a little more time so that we won't spend much time on the others. What you see is in the 1% zirconia, you see the nanoparticles, that is the scale is 100 nanometers. The particles are like less than 10 nanometer size, and those particles are distributed on the surface. And if you look at the second one, that is 2.5%, you have got more nanoparticles because the 2.5%, they are spread nicely on the surface. And if you come to 5%, you see, although you use more, but it is more agglomeration. That means, they come together, molecules come together, particles, there are larger particles forming. That means, there are less number of sites available because the agglomeration happens. With that, what it happens is, with 2.5%, you get the better activity than 1% or 5%. You can see here in this case, we tried to work out the synthesis of 12 novel indenopyrimidines using that catalyst, and the yields are 90 to 96%, and reaction time is about 30 minutes, and reaction at room temperature, and again with ethanol as solvent. Ethanol as solvent, which is a green solvent, and now the catalyst is recoverable and reusable up to 6 times without loss of activity. That means, very small change in the activity, and further, it may diminish its activity. Now, if you compare the efficiency of this reaction with the conventional one, what earlier reported, like with sodium hydroxide as a catalyst, it takes about 6 to 8 hours, and you get only 45% yield. That means, 55% of your material is, not reacted. You may have to recover and again use it, that one. But whereas the same reaction, here you can achieve 90 to 96% yield. I will take you through number of reactions similar to nature. Here you see ruthenia on zirconium. In this again, we have got 1, 2, 3, 4 component reaction, a 4-component reaction to give you the final product, the functionalized pyridines. All these are new molecules, and some of these, we have also tested their activities. In this particular talk, I'm not talking about the activities, only about the efficiency of the catalyst. Now, in this again, we had about 12 novel functionalized pyridines. Their yields are from 90 to 96%. Reaction time is 20 minutes at room temperature. And you can see those, the distribution of the molecules very nicely distributed on the surface and of the support. And if you compare the efficiency of this one with the conventional reaction with catalyst like triethylamine, which is a homogeneous catalyst. Now, 8 hours, you get 64% yield, but here you get in 20 minutes at room temperature, 90 to 96% yield. Now, look at another reaction here. Bismuth oxide on the zirconia. In this case, again, we used a 4-component reaction, that is to trihydropyranopyrazoles, and very good yields. In this case, also 2.5% bismuth on that one, and 91 to 98% yield. You can see the images on the right-hand side, that like less than 10 nanometers particle size of the active material, and reaction occurs with the quite good, excellent yields, 91 to 98%, and conventional reaction to sodium hydroxide takes 3 hours, but still you get only 35%. And you look at the efficiency of the reaction. Now, same catalyst, it is rarely you will have the exactly same catalyst work for different reactions. But here in this case, we use the same catalyst, bismuth on zirconia, for pyrazole thionones. Now, in this case, what you see is, the conditions are slightly different. In the earlier case, we used ethanol. Here we used the water, and 80% to 80 degrees temperature is quite a good reaction. With the excellent yields of 15 novel materials synthesized, 90 to 96%, and in 45 minutes reaction. 45 minutes in 85 degrees. That's quite good reaction. You can see on this one, the diagram there, the distribution of the molecules very nice. Bismuth is, it's shown in blue. You can see bismuth is very uniformly distributed on the surface, and you can see, it's quite a efficient catalyst. Now, in this case, we use nickel on zirconia. Nickel on zirconia, this is again is a very good catalyst, and reaction at room temperature with ethanol as solvent, and 18 novel materials were synthesized, and dihydropyrimidines and dihydropyrimidines have got a lot of biological activity, very uniformly distributed material, and up to 6 times you reuse that material, and with the efficiency of that is, yields are quite good. You 89 to 98%, all the materials. Now here we have the gadolinium oxide on zirconia. This particular case is a 3-component reaction at room temperature with ethanol as solvent. In 30 minutes reaction time, you get the final products. And all these reactions are at a very high atomic economy. In some cases, to be stated also specifically, like, it is a 90 to 96% yield in less than 30 minutes at room temperature, and material is recyclable at least 5 times without loss of activity. Now, vanadium is, as we know, is a strong acidic catalyst. Vanadium on zirconia, this particular thing is a novel functionalized hydropyrimidine derivatives, 1, 2, 3, 4 component reaction at room temperature. In 15 minutes, you can get, less than 20 minutes, in this particular case is 15 minutes with this derivative. With all that, you will have less than 20 minutes reaction completes with 90 to 96% yield. And then you get, you can reuse it number of times, like 6, 7 times, And here we use the yttria on zirconium. And then again, it's a 4-component reaction, quite efficient, 88 to 95%, less than 20 minutes reaction time at room temperature, ethanol as solvent. It meets all the green conditions, energy efficiency, and you get pure product and just wash it off and your product is ready for you. Here is you see the distribution of 1% and 2.5% yttria on zirconia. And in this particular case, just I want to show some other materials also. In this case, it is only zirconium, functionalized, amino-functionalized zirconium. We use this particular for the 3-component reaction to get the products. The substituted pyrimidines, quite efficient reaction, 80 to 91% yield, are very simple to prepare the catalyst, and reaction is the water ethanol mixture at 70 degrees. In 3 hours you get, which is a little longer reaction, but the efficiency of the reaction is quite good. Now here I show you, as we know, hydroxyapatite is one of the starting support material, and hydroxyapatite is the part of our bones. It is a naturally available material, and it can, you can substitute that with a number of, you can load it with different divalent and trivalent metals. Like in this case, with ruthenium loaded catalyst, calcium hydroxyapatite with the ruthenium, this particular one, 2 series of reactions, each with a 4-component reaction, you have the efficiency of both the series are quite good, and you have the 88 to 97% yield, all the 22 pyranopyrazoles we got at room temperature in less than 30 minutes time. If you compare the efficiency of the same reaction from the literature using the reflex conditions and stannous oxide as catalyst, and in that particular case, you see that, the 1 to 2 days to get only 80% yield. Here you are getting the less than 30 minutes, 88 to 99% yield at room temperature. Here we have the hydroxyapatite loaded with the magnesium oxide. And in this particular case, we see a 3-component reaction with 90 to 98% yield and very good efficient system. In less than 25 minutes reaction time, you get the reaction completed and with the good yields, as you see. And now I'll try to show you some other ones, like in this case, we use the hydroxyapatite with nanocellulose. Nanocellulose, as you know, biopolymer, natural polymer, and this is quite efficient, this particular reaction. In this one, although it is a 3-component reaction, it's only a simple condensation reaction, but still, because the material is new, I tried to show you here. You can see 12 novel triazolidine derivatives. We have 90 to 96% and 15 minutes reaction time at room temperature with ethanol as solvent. That means, it is quite good product yield, Now we have in this case, we have a 3-component reactions. We use another natural material, chitosan on calcium hydroxyapatite, similar to earlier we had the nanocellulose. In this particular case, you can see that diamino pyrene dicarbonitriles, we have synthesized a series like 12 molecules, 12 library of 12 was synthesized with 86 to 96% yield and less than 30 minutes. And it's quite good, in this sense, efficiency is good. And the material is recyclable up to 6 times. You can see in this instead of particles, you have got the rod-like structures of the material that is on the, because natural polymer, it is not particles, it is like small long ones, And here I show you another type of materials. Instead of hydroxyapatite, we use the fluoroapatite. Fluoroapatite means so it contains fluorine. The presence of fluorine makes the reaction have the material have distinct properties. In this particular case, we had the 3-component reaction of synthesis of the triazolopyrimidines and dihydrotriazolopyrimidines, and you have that 90 to 96% yield in less than 35 minutes. And all the materials were new materials synthesized. And as you see in this particular case, 98% atomic efficiency and 100% carbon efficiency. All the carbons are there in your final product, and 98% of the molecules or atoms are there in that. That means very little wastage in this particular reaction. As you see that, you see the on the top right-hand side, how the distribution of that fluorine is there on that, and you have the bismuth is there, and bismuth and fluorine are very evenly distributed on the surface of your catalyst, and it's quite efficient. That gives you the efficiency. Now you see the nickel oxide on the fluoroapatite, and very similar that, now the support material is different. And with that, you have the 4-component reaction giving you the ethanol. And this is not at room temperature. We did it at 50 degrees, but reaction in less than 40 minutes. And catalyst is recyclable up to 6 times and quite efficient reaction. And you see the yields there, 92, 96% yields. And then here, you got some other material like vanadium oxide and the fluoroapatite. Vanadium oxide and fluoroapatite, if you see the nature of the catalyst, how it is loaded, very uniformly loaded catalyst and very efficient catalyst. Again, 90 to 97% yield that of your thiazolopyrimidines. And you see this one, we have got 3 different series have been synthesized, 3 different series all with very good efficiency and good yields. And this one is quite you can see that catalyst is again recyclable up to 5 times. You get the pure product in each case. I take you to different materials we use now. Here in this case, we use samarium loaded on fluoroapatite, and then that loaded on the multi-walled carbon nanotubes. You see that, what it happens, even the multi-walled carbon nanotubes can act as catalyst, samaria can act as catalyst, and fluoroapatite can act as catalyst. But the combination of that is the one in which is giving you the supreme efficiency. That's why you have to take the trouble of putting that together. In this particular case, we have this one for a 2-component reaction, of course, but why I showed this one is, because of the efficiency of the reaction. You see 80 to 96% at room temperature, ethanol as solvent. In less than 10 minutes, your reaction is finished. Less than 10 minutes, you get, it is worth taking the trouble of preparing that catalyst. I will show you another catalyst and similar one. Here in this case, titanium fluoroapatite loaded on the multi-walled carbon nanotubes, and this particular is used for the 3-component reaction where pyrazolophenolines, quite efficiently, they are prepared in less than 20 minutes with 91 to 95% yield, and you see that happening at room temperature, and material is very effectively recyclable. And I will show you another material that is a hydrotalcite. Hydrotalcite is a very cheap material what is used in the face powder, we use, talcum powder, what you call, that contains this hydrotalcite. This hydrotalcite, you can modify that in various ways, and you can, in this particular case, we loaded magnesium, 1:1 ratio of magnesium vanadium carbonate on the hydrotalcite, and this particular three-component reaction, quite efficient at room temperature. In 45 minutes, you get the products, and 89 to 94% yield, and reaction takes less than 1 hour, but efficiency is good. Now, if you compare the conventional reaction with sodium hydroxide reported, it takes 8 hours, only giving you 54% yield, but here you get the efficiency is 89 to 94 yield. And another one is, zirconium and vanadium carbonate on the hydrotalcite. In this particular, we used that 4-component reaction, multifunctionalized benzenes, and we have that 93 to 98% yield in water, and it is water as solvent at 80 degrees. You get the reaction, and in 1 hour time you get the excellent yields. The same reaction in sodium hydroxide at same 80 degrees, and it takes 6 hours to get you 30% yield. Now you get almost 93 to 98% yield. And here this particular reaction, we use the gold on magnesium oxide. It's quite a simple catalyst. We use the 1% gold on the gold oxide. Finally, it will be gold oxide. And in ethanol at about 70 degrees, the reaction, you get the 4-component reaction, quite efficient. 2 series of reactions have been done, and both have got very good efficiencies. And one case 85 to 95, other one slightly low, 80 to 86%. All the reactions are quite efficient, recyclable materials compared to the conventional reaction, which takes 7 hours, and with 30% yield, here you get almost 90% yield in less than 45 minutes. And in ethanol, and it's quite efficient. Now I take you through some other materials like graphene oxide. Graphene oxide in this particular case, amine functionalized graphene oxide. In this particular case, we use on 4-component reaction. The 4-component reaction quite efficient to give the products 93% yield. And then, it takes a little longer, like 2 hours, but at room temperature reaction occurs and material is recyclable up to 3 times, but the reaction is quite efficient. And here I show you another simple example, may be useful for anybody. Most of the times we use the amination of the benzene. Normally you can't do it directly. The efficiency is very poor. Normally people use nitrobenzene to convert that into aniline. But in this case, we can, benzene, which is the very cheap material, can be very effectively converted to amine, with 100% selectivity. 100% selectivity, that is important, Here we get 77% conversion with manganese oxide and reduced graphene oxide. It's quite an efficient reaction, and although it is a different class of reaction, but still I thought it will be interesting for the many people. Here I show you some other type of materials like, these coordinated complexes. In this particular case, we use the ligand coordination complex with the cobalt and cadmium, and to synthesize the pyrozoles, 4-component reactions, quite efficient conversion. Both the catalysts did quite good job. Both have shown, although slightly, the cobalt is slightly efficient, marginally efficient, but both have got good efficiency, 90 to 98% yield. And then, in less than 20 minutes at room temperature, and it's quite a good catalyst and recyclable up to six cycles. Now, let me show you some other materials. Now here, this is another aluminum coordination complex, and for the synthesis of benzoquinolene carbonitriles, and it's a 4-component reaction, and at room temperature, ethanol as solvent, very good yields, like you see 90 to 96% yield. And this is like MOFs, MOFs is the metal organic structure frameworks. These are quite efficient. And in this particular MOF, we use this MOF. MOFs are used in many other, for many other purposes. There are very few cases where they are used now. We have 91 to 96% yield in less than 40 minutes at room temperature. Okay. Now we have another example. In this particular case, we have the cobalt cadmium MOF, and this again for benzopherophenolines, and yields are in quite good, and room temperature, ethanol as solvent, a 3-component reaction, very efficient conversion, less than 25 minutes. Now I want to show you a couple of different materials than what we did. It is like eggshell. The eggshell, you see that eggshell is a normal egg, you make that one from the eggshell, you condition that. That is used for the conversion of a 4-component reaction. The eggshell for the 60 reaction has got some disturbance. 93 to 98%. 45 minutes and 98% and 100% carbon efficiency. You can see there is a very nicely distributed materials because you have got the number of calcium and calcium. Calcium is the main component of your eggshell, and that itself is acting together with small amount of sodium. This one is, many people have reported using the clays. In this particular, using the red brick clay, almost, all the red bricks, brick clays, any part of the world, will have more or less similar composition because, they have to be intact, and when you go through the similar processes, and if you look at this, they contain many oxides, silica oxide and iron, aluminum, calcium, and magnesium. These are mainly the silica and iron are the oxides there, and these ones, they act as very combination, like a mixed oxide catalyst. You have a 4-component reaction giving you 91 to 96% yield, and quite a better substituted all derivatives, and you see that, you have it's the recyclable again, although clay, it's not a great thing. Its efficiency is quite good, and you can see, how you can use choosing the right catalyst, how can achieve excellent results. Hello, can you hear me? Hello?
Yes, sir.
Hello?
Yes, sir. Yes, sir. We can hear
I'm
you.
coming to the conclusions. And now you can see that, we have the mixed, have shown the number of examples from our research group, using mixed oxides and the nano composites as the materials, we can do at moderate conditions and with excellent yields and the good solvents and all that in a very short reaction times, and materials are recyclable, fulfilling all the green chemistry principles. Okay, now, these are some of our postdocs and our PhD students, but not everybody is here, and all my papers, although I have shown my name as, just to indicate it is our work, our papers indicate the first author is the person who actually did the work, and his name is there, but he's the main author, and I will be corresponding author, but otherwise, you see all our work, and a lot many people's work, you can see the of the work, and our funding agencies, and finally our university I have to thank, and I want to thank you for your attention. And the bottom that it says, for all the young people, who are aspiring to be great scientists, they should look at, a man can succeed at almost anything for which he has unlimited enthusiasm. That is what is important, is, you have to have the zeal to achieve your goal. And thus it's always said, aim high, aim at the sky, at least you will be on the treetops. And that's why, aim high, you can achieve great success in your life. And this is our Durban beach and harbor area. And then this is our soccer stadium. And again, this is the Durban city. Thank you for your attention.
Thank you, sir. Thank you for your informative and most elaborative lecture on applications of nanoparticles, particularly in green synthesis. They are very interesting works, sir, even using by red brick clay also, and also used in organic synthesis. That is very interesting, sir. Now I would like to thank you. Thank you for your sparing time, sir, from
You're welcome.
Schedule.
Thank you, Ashok. Keep well.
Sir, thank you, sir. Thank you.
So thank you so much, sir, for your time and presentation.
Thank you. Welcome.
Sir Ashok, sir.
Okay.
Raju Janapredi.
Next, I think we'll go for it.
Now it's time to invite a young chemist, Dr. Raju Janapredi, working at Usmania University, to talk on beta iodovinyl sulfones as versatile building blocks in organic synthesis. Dr. Raju Janapredi completed PhD from Central University and completed four PDFs from Taiwan, Japan, UK. He published 33 publications in peer-reviewed journals. He is a member of, he is Associate Fellow of Telangana University, member of Royal Society. Now, he is carrying different research projects. Now I invite Dr. Raju Janapredi to deliver lecture.
Good afternoon, everyone. I hope I am audible. Hope
Yes.
all of you hearing.
Yeah, you are.
Yes.
So able to see my slide with the cursor, possibly.
Yes.
Okay. Good afternoon, one and all again. Thank you, sir, Vasudharity sir, for your kind introduction about me. And I would like to thank you, first of all, Professor Leelavati madam, for initiating to give a talk in this symposium particularly. And also I would like to thank Professor Ashok sir, who always support me and encourage me in many aspects, particularly research, and also convener of the today's symposium. Also, I would like to thank Professor Sarsi Jameo. And I would like to start with my title of the talk is today is the beta iodovinyl sulfones, a versatile building block in organic synthesis. So I hope I will be justified the title end of my talk, how it could be versatile. So before I start, I will give the brief introduction about the beta iodovinyl sulfone, particularly the beta halovinyl sulfones. So when you are looking at this particularly beta iodovinyl sulfone, if you see carefully, this beta iodovinyl sulfone having the multifunctional compounds. At that end is the iodo, and other side exactly opposite configuration sulfone. So keeping in this mind, this would be useful for the various organic transformation for synthesis of the sulfur compounds as well as the heterocyclic compounds. So we tried a careful research only one research was report the applications of the beta iodovinyl sulfone or else beta halovinyl sulfones. In 2006, the one is reported just nucleophilic substitution reaction of the beta iodovinyl sulfones. However, there are dozens of methods have been reported for particular synthesis of the beta halovinyl sulfones. But there are a lot of applications are much limited except this one. So with this keeping in mind, here I've shown this some of our applications of the beta iodovinyl sulfone. So we have prepared various analogs like benzopherones and pyrazolopyrimidines, and of course dithioalkenes and beta iodothiosulfones. So I'm going through details one after others for synthesis of the various analogs using the beta iodovinyl sulfones. So particularly, we started as initiation of the mono and bis thiosulfonation of the beta iodovinyl sulfones using this simple thiol, which is the cheap and commercially available. So it could be able to synthesize 1,2-dithioalkenes as well as the 1,2-thiosulfonalkenes. So if you see the careful literature survey, there is only possibility of the preparation Z configuration of the 1,2-dithioalkenes. So there are two among the various methods, only the two popular methods is described here, which will be able to synthesize the Z1,2-dithioalkenes. So you can see here various representative examples of the combination of the bis thiolated alkenes. One is the antifungal agent, another one is the dithione biologically active molecules. And more importantly, the molecules are exhibit like a metal-based bis thiodiene complex, metal complexes, which will be useful in organic transformation. So based on this strategy, you're looking at the beta iodovinyl sulfones will be also very good precursor to synthesis of the 1,2-dithioalkenes. So here our work will be initiated with the using the thiols in the simple K2CO3 condition. So be able to synthesize the E1,2-dithioalkenes, so which is not reported in the earlier methods. So with the first time we were able to prepare the corresponding E1,2-dithioalkene, which will be mostly symmetrical molecules, which means both are the thiols will be the same. So alternatively, we are able to synthesize also 1,2-thiosulfonyl alkenes if we switch into the different condition. Only it is the reaction is the solvent dependent. When we use the DMSO, we are able to produce this type of products. Whereas if you are able to use the methanol, we are able to see the Z1,2-thioalkene, which will be further transformation performed in the DMSO, which we are able to synthesize which people are reported routinely that Z1,2-thioalkene, which most of them are unsymmetrical. Unsymmetrical in the sense that where we can one sulfone introduce the first and other type of sulfone can be introduced the later. So therefore it could be unsymmetrical 1,2-dithiosulfones. So in this strategy, we have established the optimization reaction condition. Here is shown the optimize the reaction condition. So you can see, observe the carefully, the reaction can be performed in the DMSO and DMF. In the DMSO, DMF, where we have observed only the dithiosulfonated product. So we could not observe anything like Z or E monothiolated product. Simply changing the condition, simply changing the solvent, keeping the same base, changing the solvent instead of DMSO, the best reaction condition turned to be the DMSO. Within the short reaction of time, in 15 minutes, we are able to produce the 93% of the desired product. So later we have seen the other solvents like methanol, acetonitrile. Here we can see the stereodivergent products. So where the methanol is there at 0 degrees centigrade, we are able to see the Z isomer. We can see here Z isomer, Z4A we can able to isolate with minor amount of the E5A. So alternatively, instead of methanol or else DMSO, we seen this other solvent S2-nitrile, we have obtained the contrast product like E isomer. So simply, the reaction is totally dependent on the solvent. So therefore, we gone through with the various substrate scope, particularly using the DMSO. We have screened the substrate scope with the different substituents like this, and para substituent and meta substituent and ortho substituents. So all the substrates will proceeded very well to provide the desired product, and almost we are obtaining the good to high yield. So interestingly, when we use the alkyne thiol, particularly mericaptobenzene, so we obtained only the optimum yield in 60%. We observed for the observed the enantiomers of the EZ stereoselective isomers of the EZ with 5:1 ratio. So then after changing the thiols, we also see the beta-iodo, beta-bromo vinyl sulfones. So here is the results are summarized. Various results with the using the beta-iodo, beta-vinyl thiosulfanes. So all our reactions went well to provided the 1,2-diethylsulfonate products. So whereas alkyl substituted and heteroaryl substituted will also produce the desired products. And interestingly, we have here 3-chlorine substituting in the molecules also will able to produce, and also sterically bulky molecule like naphthyl system, 2-naphthyl system also be able to produce in the moderate yields. And also be able to see using the different type of the bromo alkynes, bromo, beta-iodo, beta-bromo vinyl sulfones also able to produce the desired product in the 77% yields. In contrast, when we used the alkyl instead of aryl here, when we used the alkyl, we could not obtain this desired product. However, we able to see other type of product. I will show you in the later slides. So keeping in the mind the solvent effect in the reaction condition, so we screen the reaction using the methanol in the K2CO3. So I just shown the optimized reaction condition at 0 degrees. So we have screened the various substrates group. Variety of thiols are incorporated in the reaction condition and provided the desired product almost high yields. So as I told you, the reaction will be provided the way you have seen in the, instead of providing a 1,2-thiolated product, be able to see only the monothiolated product instead of alkyl group. So we able to provide only monoalkyl product in the case of DMSO as well as the methanol. Instead of methanol, we are able to see the reaction condition in S2-nitrile, and also be able to prepare few analogs under these conditions. So we able to synthesize the 3 analogs of these under these conditions with the ZE selectivity of the desired 1,2-thiosulfonyl alkenes. So we can see here in the methanol and as well as the S2-nitrile produce the different stereoselective products. These products be able to go undergo for the desulfonation and thiosulfonylation of the products. So how we confirm the structures? The structures of these molecules further established by the single crystal analysis. So you can see the single crystal analysis of the compound 4Z. We can show same side of the sulfur moieties, and of course Z4K of the molecule. You can see the sulfur's atoms are the same side. That way you confirmed by the selectivity, stereoselectivity of the compound. So it also confirmed by the E analogs and E5B. And the single crystal of the E5B established by the stereochemistry. You can see carefully the sulfur atoms are opposite to each other. That way we confirmed by the E selectivity of the product. So overall, all the compounds is established based on the NMR analysis as well as the single crystal X-ray data analysis. Further, we want to utilize this monothiolated product for bisthionated products. So the optimized condition, as is shown in the bisthionated, we utilized it here using the different thiols. So you can see these are different thiols under these conditions using the sulfonyl, monosulfonyl compounds, or else 1,2-thiosulfone alkenes we treated with the thiols in the presence of base, simple base. We will be able to produce the desired 1,2-dithioalkenes. So here, interestingly, we are able to synthesize various unsymmetrical compounds. So various unsymmetric compounds we obtained, including the variety of aromatic thiols, aliphatic thiols, and also we also see the reaction instead of jet, we able to see E also. So alkenes were treated with the thiocresol in the presence of base. In DMSO, we able to provide the other alternative stereochemistry. You can see overall summarize here where you can take the Z isomer of the starting material, it will be provide the Z isomer of the product. Alternatively, when you have taken the E isomer of the substrate, you are able to produce the corresponding the E isomer. So in this overall, in this results, we are able to synthesize both EZ12-dithio-1 alkenes. So looking at the gram scale reaction in synthetic from point of view, we perform the reactions at the gram scale. Two setup of reactions we performed at 81% yield, and of course the decent yield we obtained at gram scale reactions. So when you use 1.41 grams of the corresponding product, and also corresponding Z isomer of the 1,2-dithiosulfonyl alkenes also produced in the 72% yields. So these results will be summarized with the various control experiments. You can see that we performed many control experiments. However, so some of the control experiments we have shown here. So the control experiment is begin with the using the keeping in the mind that dithiol may be one of the reactive participants, but we tried with the using the disulfide, but we could not observe the desired partnership. So they ruled out that the intermediate may not be disulfide. So that in order to understand the reaction, whether it is proceed the ionic mechanism or radical mechanism, so we treated with the reaction with the radical scavengers like BHT or TEMPO, we treated with the under standard conditions. So, however, we obtained the decent yield. Therefore, it could be again ruled out the reaction is not a radical reaction. It might be proceeding through ionic mechanism. So we are able to prepare the deuterated analog of the beta iodovinyl sulfones. We easily prepare the deuterated compound from the corresponding starting materials. Then the starting treated with the beta iodovinyl sulfone under standard condition with the thiocresol. So we can able to see the 100% retention of the deuterium. That in sense that is the corresponding hydrogen may not be playing any role. So therefore, it will be the hydrogen may not be played so by incorporation or the retain of the deuterium. So with this control experiment, we provide the possible mechanism here. So the reaction may proceed like this. So there are a lot of transformations are involved to provide the changing the condition, changing the solvent. So overall, this reaction condition is the independent on the solvents. So we're taking the vial. So the simply first addition of the thiol. So simply Michael addition, it will provide this type of the analog. So anion. This anion will be resonate with the corresponding sulfones. So this will be forming in this kind of transition state, which will be clockwise direction. It will be sterically less hindered molecule, staggered molecule will be provided. By loss of the iodine, it will be provide the corresponding EA. So this EA will be further treated with the other thiols. It will be formed this kind of another addition of the thiol, and it will be form another type of the staggered with the preference of between the steric indents of the molecules. So the repulsion between the phenyl and the sulfones, it will be provide the rotation of the molecules. It will provide the corresponding transition state model. Finally, it will be end up with the corresponding the 1,2-dithioalkene, corresponding E3AA product. Similarly, in methanol, the methanol will be protonated. So that is obvious. So where the protonated solvent is there, the ion will be protonated. Subsequently, where the methanol will be regenerated, methane ion, this corresponding sulfone ion, so will be regenerated in the presence of traces amount of the methoxide ion. So this ion, and where we have shown this ion will be the, maybe they are in the maybe different geometrical isomers. So that way the compounds are providing the different type of the E and Z isomer. So this is the information about the possible mechanism. So we have an argument with the current reviewers that the mechanism is the need to revise. So this will be under revision of this paper. So we need to revise. They need a little bit more evidence to publish this work in JOC. So therefore, this work is under revision. So continuously utilization of this beta iodosulfones, we also seen the synthesis of the various beta ketosulfones and beta ketothiasulfones. So in the literature precedents, there are many methods for synthesis of the beta ketosulfones. So in the U and co-workers is reported this type of methods using the azides, vinyl azides in the sulfonyl hydrogen under the TBHP conditions, and also using the beta keto ester group. So this is the CF3 DOST will be used in the simple condition and providing the beta ketothiasulfones. More recently, Zhu and co-workers used a simple alkene and thiosulfonates in the presence of the copper salts in the bipyridal. It will produce the corresponding beta ketothiasulfones. So keeping in this mind these methods, so be able to synthesize similar analogs, similar either beta ketosulfone or beta ketothiasulfone using the beta iodovinyl sulfones. So we initiated the conditions reaction simply treating with this some various conditions we performed, but we found this sodium acetate is a simple method to perform the reactions. So in the sodium acetate in the DMSO water in the 9:1 will provide the desired product beta ketosulfones. So when we did that, we thought that this will be reaction will be generate the corresponding indirect enolate ion. So indirect enolate ion we can be able to trap or not. So that way we tried in the using the corresponding electrophile, that is thiosulfonate. We use this thiosulfonate to trap the indirect enolate where it will produce the indirect enolate. That will be discussed in the mechanism aspect in the later slides, and also will produce the corresponding beta ketothiasulfones. So we have screened the various optimized conditions for the beta ketosulfones using the beta iodovinyl sulfones. Simply the reaction is obtained a better yield in the sodium acetate DMSO, or else DMSO water also provided the equivalent amount of the yield in the 3 hours of the reaction time. So subsequently, we performed the substrate scope of the synthesis of the beta ketosulfones using the variety of the beta iodovinyl sulfones. So you can see here, variety of the reactions rate products is formed beta ketosulfones under the standard conditions. The almost all we obtained the quite good yield irrespective of the substituents. So therefore, we able to synthesize different type of the analogs of the beta ketosulfones. So the reaction will be having the troubleshoot at the using the alkyl beta iodovinyl sulfones. The reaction very sluggish, and it provide the prolonged reaction time. It will be provide the instead of the desired product. The mixture of product we can see by TLC of the using the where we use the instead of aryl group, instead you use the alkyl group. So the latter we further optimize the reaction condition for the synthesis of the beta ketothiasulfone. As I mentioned that this will be act as the indirect enolate. This indirect enolate, keep in mind, we trapped with the using the thiosulfonate. So the thio group is coming from here as the sulfonate. So for this one, to understanding the reaction condition, we perform the different various conditions and be able to see the best condition using the one equivalence of the beta iodovinyl sulfone, 1 point equivalence of the thiosulfonates, and in the presence of the sodium acetate 2 equivalence in DMF, the solvents we use 91% of the desired product, that is beta keto thiosulfone we obtained. So then we carefully examine the substrate slope using the various type of the various substituents, either beta iodovinyl sulfone or thiosulfonates. The results are summarized here. All the reactions are proceeding very well, irrespective of the different substance. There is a little sacrifice yields are there on the substituents. Otherwise, the reactions are very well. And provided the yields with the different products and various heteroaryl, heryls, all will be able to survive. Except where we use the benzyl thiosulfate, where we use the alkyl group here, that will be, reaction will not produce a desired product when we have it using the S-benzyl thiosulfonates. So then we tune the reaction, whether it is possible the gram scale reaction. Since it is a synthetic point of view, very important to understand the reactions at the large scale reactions. So the reactions can be easily performed at a gram scale reactions, and the yields are quite good, and compared to the small scale reactions, and we able to provide the gram scale products of the desired corresponding the beta iodovinyl sulfones. Of course, we perform the couple of examples using the different beta iodovinyl sulfones. Okay, further we perform the reaction. We would, in order to know that the reaction mechanism aspects of the reaction conditions that we performed. So we perform the various types of the control experiments. So we assume that this kind of ketone may be possible. Methyl ketones is the precursor in the reaction medium, which will be trapped. As I mentioned, that the indirect enolate. So therefore, we have able to see this reaction condition will be provided the desired product. So, however, we have not seen any desired product when you use the methyl ketone. So subsequently, we also seen this beta keto sulfones, whether it will be produced the desired product. Fortunately, the beta keto sulfones is the key intermediate for to provide the beta keto thiosulfones and able to produce the corresponding the product in 50% yield. So we also seen the reaction. We taking the mixture of the two independent beta iodovinyl sulfones and perform the reactions. What will happen? So the reaction we've seen the 4-toluene and bulky group 2-naphthalate, and the key intermediate that we observed in the proton NMR with the ratio of the beta keto sulfone as well as the estate corresponding vinyl estate of the beta alkene with the ratio of the 2:1 and 3:1. So this we observed carefully in the proton NMR analysis. So this, when the further we ruled out the mechanism based on this beta vinyl interestyl one intermediate, and you can see the possible mechanism in the formation of the 1,2-oxosulfonylation. Initially, the estate may attack on the Michael type addition will takes place on the beta iodovinyl sulfones, and it may provide the desired possible product A. This intermediate further enolate will be back, and it will be iodine will be kick off, and you can see this corresponding intermediate that we observed in the NMR by our control experiments. So this beta iodovinyl sulfone will be treated with the aqueous condition. In the aqueous DMSO or aqueous DMF, it will be cleave the ester group and forming the enol. That enol will be further transformed the corresponding the beta keto sulfones. This enol will be trapped by these thiosulfonates, and C-carbon sulfur bond may form. So it will deliver the desired product of the beta keto thiosulfones. Alternatively, the mechanism also may be proceeded using this corresponding intermediate A, where we can use this same thiosulfonate and it will trap this ion and further alkynyl formation. So it will be provide the intermediate C, and upon hydrolysis in the aqueous medium, so acetate may cleave the enol will be converted into the corresponding beta keto thiosulfones. So this is the synthesis of various type of the sulfur analogs we prepared using the using the variety of the beta hydrovinyl sulfones. Next, our attention is turned. These beta hydrosulfones can be utilized to synthesize the heterocyclic molecules. So based on that idea, we able to synthesize, we able to see the strategy. We are able to arrive the strategy. You can hear, so you can see here. So retrosynthetic analysis is provided here. In this, the reaction will be performed, the Heck reaction, and followed with the oxo-Michael addition. So using the beta hydrosulfones, and simply when you use the 2-bromophenol, 2 iodophenols, you can use. So first Michael addition will be take place in the for construction of the CO bond. Later, the intramolecular Heck type reaction can be performed using this intermediate B, and it may form the corresponding benzopherophenolines. So while working on this project, so another group is reported, Benwell and co-worker is reported at the same time, is a similar strategy using the different type of palladium catalysis in the copper as the oxidant under dry DMSO. It will be able to produce the different type of the benzopherophenolines. So then we perform the reaction in the 2 steps able to can be performed in one part operation. So the reaction proceed very well. The Michael addition as well as the Heck reaction conditions smoothly proceeded, and under the various conditions, we able to see the best condition using the palladium acetate 10 mole%, and of course triphenyl phosphine 20 mole%, and cesium carbonate using the cesium carbonate for the Michael addition 2 equivalents in the DMFO as the ideal solvent at 120 degrees. So we able to obtain the desired product of the corresponding benzopyrene in 86%. So once we have the right optimized condition or best optimized condition in hand, so we elaborated the scope of the reactions using the different beta hydrovinyl sulfone as well as the beta halophenols. Both we screened carefully to perform the reactions. So you can see summarize the results using the various beta hydrovinyl sulfone as well as the 2-bromophenols. Not only 2-bromopyridine, pyridine substituted 2-bromo-3-phenol, 2-pyridine substituted bromophenols also can be performed. So of course, we for various reactions, we can see various substrate scope with using the different substituents and beta hydrovinyl sulfones, and some of the analogs will be confirmed by the single crystal X-ray data. And the substituent at 4 position, we are able to provide the desired product quite good yield, and the substituent other position, 4th position of the other functional group instead of the sulfone, another functional, we be able to see the desired product. So like that, we able to synthesize naphthyl derived, heteroaryl derived, and various analogs we able to synthesize, including the aliphatic like cyclopropyl group. So, and also we able to synthesize pyridine fused benzopyrans also, pyridine fused analogs also be able to synthesize using these conditions. And we have a problem with using the different substituents with the alkyl group in the different substituents. Look at this one, the butyl group is here. So we are unable to produce the desired product. So we have a mixture of products observed under the present reaction conditions. Further, also we have screened using the different bromophenol. So while look at this in the previous slide, we have changed both of the. Now we restricted the 2 different kind of bromophenols, and we able to produce the diversity substituents of the corresponding the 3-sulfonyl benzopherones. So for your information, I can tell you that these 3-sulfonyl benzopherone is the most of the biological active molecules are present, and of course they are used in the medicinal relevance molecules. So since so many people are reporting synthesis of the benzopherones, so I can claim here that this is the one beautiful strategy to prepare the corresponding sulfonyl benzopherones, which can be utilized for the medicinal aspects. So again, we perform the control experiments, is it here? So to understand the reaction mechanism, first we tried with the without bromo. There is no reaction. We able to see only intermediate. And also we tried with the standard condition, bromo instead of the, here we eliminated bromo, only phenol we left it here, and here we bromo benzene we taken here, so we could not detect the desired product. We observed only this kind of, we could not obtain this kind of growth of the product, we could not detect it. And we assume that the alkyne may be possible of intermediate. So therefore we perform the reaction phenyl acetylene. So we able to see the provided the desired product, which is the reported in the literature. So here the geometry of this double bond is the restricted here. So the geometry we observed in our product formation is the E configuration. Here is the people is reported with the under this condition the Z isomers. So we able to synthesize the Z isomer of this vinyl ethers. Then we performed our standard condition. Surprisingly, we able to see the product in 13% only. So that way we can rule out. So the geometry of the vinyl ether is the essential to perform the head type reaction for the cyclization. So this yield may be resulted the interconversion of the geometry that we relieve the 13% of the desired product. Further control experiments, we assume that usually this type of alkynes will be formed under basic condition. This was reported in the literature. So we able to synthesize this kind of phenyl tosyl alkene 7 compound, and then we perform the reaction using the 2-bromophenol under standard condition. But however, we could not obtain the desired product of the 3-sulfonyl benzopherone. So from here, we can conclude that the reaction might not proceed using this phenyl tosyl sulfones. The strategy may be involved in the alternative vinyl ethers. And also we used the corresponding deuterated vinyl ethers treated with the bromophenols. So it is the complete the reaction is the proceeded under a little bit slow. So because of the deuterium, the rate of the reaction is determined Kd by Kh with the rate of the 1.5. So the role of the deuterium or role of the olefin is playing an important role in the Heck type cyclization. So this is the mechanism. The mechanism is outlined here on the basis of the control experiments as well as our results. So initially the mechanism of Michael addition will be takes place, and of course this is the elimination will be formed. This is the vinyl ethers is the form. This is the key precursor for the cyclization. Under the palladium condition, as you know, the oxidative insertion will be takes place. So this is the bromo palladium insertion will be takes place. Pi bond complexation will be takes place. That the close together with the pi bond complexation with the olefin of palladium, and the carbo palladation will be takes place. Finally, hydride, beta hydride elimination lead to the desired 3-sulfonyl benzopherone will be delivered smoothly under these conditions. So with the success of this work, we continually exploring these beta iodose vinyl sulfones to synthesize the variety of heterocycles. So you can see the starting metal is the same, that is the beta iodovinyl sulfones. We change the substrate, that is N-amino pyridinium salts treated with the acetonitrile in the 90 degrees, we able to the desulfonylation product we able to see. Pyrrolopyridine. Pyrrolopyridine simply 2 substituted pyrrolophenol we obtained. And we want to see this sulfonyl group in our products. So for that one, we tune the reaction condition. How we tune the reaction condition? Instead of this N-aminopyridine, we able to synthesize N-tosyl ylide. This is called as a ylide, N plus N minus. This ylide will be undergo cycloannulation type, and we able to see this desired sulfonyl products. So you change the substrate, simply change the substrate with the minor variation in the condition, be able to see the different type of products. So once we have the reaction product in hand, explore the optimize the reaction condition. We perform the reaction using the different condition and using the simple base here, just K2CO3 sufficient enough for the annulation in the formation of the 2-phenyl pyrrolopyridine. So the reaction is the best yield very obtained using the 1.5 equivalence of the substrate and 1.5 equivalence of the K2CO3 in acetonitrile at 90 degrees. Within the 1 hour, we are able to provide the desired product in 88%. So we further, obviously in the synthetic organic chemistry required to show the substrate scope. So then we perform the substrate scope of the reactions. So losing here, the sulfone is going away from the substrates. Under these conditions, we are able to provide the different kind of the 2 substituted pyrrolopyridine derivative in moderate to good yield under all the cases. And we have used a variety of aryl groups here, you can see, and naphthyl, and of course heteroaryl, and also provided the desired product, including the cyclopropyl substituents. So it is surprised to see us. So when you have the butyl substituents, the sulfone groups is retained using the same starting material like N-aminopyridine. So this is the exceptional case to deliver the product using having the sulfone group. So we are able to synthesize the 2 different analogs of the sulfones in the moderate yields. So we also seen instead of the iodine, we also see the bromo effect in the reactions. So we able to see the moderate yield. So that may be possibility of the degradation of the starting material to the low yield of the desired 2-phenyl pyrrolopyridine product 3A. And further, using this ylide, N-tosyl ylide, so where it is the retained sulfone group, so the optimization condition is performed. So the optimization condition is proceeding smoothly. So where you have the 1 equivalence, 1.5 equivalence of the substrate, 1 equivalence of base. Here is the required little harsh condition, that is a chlorobenzene at 120 degrees. And of course, the reaction is proceed slowly. It took 36 hours to completion. The desired product is obtained in a 78% yield. And the structure of this molecule is further established by the single crystal X-ray data. And further, we have seen this substrate scope of the reactions of the 2 substituted 3-sulfonyl pyrrolopyridines using the same starting material, N-tosyl ylide. So here is the interestingly, the pyridine is going away and the sulfone is retaining, and tosyl also going away, and various derivatives are able to prepare the 4 substituent derivative here, 2 substituent derivative here, naphthyl derivative, and of course you can see this heteroaryl also provided. But however, thiophene derived compound is obtained in 20% yield, less than 20% yield, but the NMR shows the impurity. And we are able to synthesize the sulfone compounds of the aliphatic substituents as well. And also we have seen these different sulfonyl groups, also able to synthesize, including the aryl, naphthyl, thiophenyl, 2-thiophenyl derived in the good to moderate to good yields. And instead of the iodine, bromine also we reaction performed with the N-tosyl ylide. So we are able to obtain the corresponding desired product in 60% yields. So subsequently, in order to understand the synthetic view of the reactions, we able to perform the ground scale reactions. So the ground scale reactions also smoothly proceeding the desired product. So even we have the small scale reaction, the yields is almost the same at the ground scale reactions. So with 3A product we obtained in the 76% yield, and the sulfonyl derived out of the same obtained in the 1.3 gram of the in 74% yield. So again, to propose the mechanism, it is required some kind of control experiments. So the control experiments we perform using the deuterated beta hydrovinyl sulfones treated with the N-aminopyridine. So here you can see this deuterium is replaced by the hydrogen. That means this will be involved in the cyclization or cycloanylation process. And where we use the alkane, thioalkane, and the sulfonyl alkane, we use. So here is the alkane, no reaction. And when you have is the thioalkynes, the product we can see 20% yield only, the loss of sulfonyl. And sulfonyl groups yield provide the desired product. And with sulfonyl, without sulfonyl, the ratio of the product can able to see 23% of the without sulfonyl, 56% of the with sulfonyls. So by this control experiment, we conclude that this is the sulfone alkynyl sulfone group possibly is the key intermediate for the formation of the desired product. Further, changing the ylide, intosyl ylides, we perform the similar control experiments. Surprisingly, we could not observe any reaction using the thiol, where we observed in the case of the aminopyridine. One aminopyridine, we 20% we observed. Here also we can see here N-tosyl 1, there is no reactions, where you can see the product we observed in aminopyridine we used. So he can also see this. Surprise, here the deuterium is there, I missed it. So the deuterium N-benzyl is there. N-benzyl substituents of the compound will be, traces of the product will be formed instead of the tosyl. If you change the benzyl, the product is observed tosyl, benzyl group. Instead of tosyl, the product is only traces of the desired products could be observed. So based on these control experiments as well as the results, we can conclude the mechanism. So the mechanism is the simple and straightforward kind of Michael addition, and followed by the simple cyclization. Simple, the ring closure reaction will be performed, and aromatization lead to the desired product by loss of this sulfonyl group. So changing the substitute N-tosyl group, and you can see the cyclization will be takes place here. The pyridine ring is disturbed here, and subsequently the loss of the alkene bond will be, HI will be eliminated and forming the 3-sulfonyl pyridine. Further aromatization will be takes place, the mobilization of the hydrogen, and the N-tosyl group is leaving to produce the 3-sulfonyl pyrazolopyridine will be formed. So overall, depending on the substrates, we are able to synthesize the 3 unsubstituted product and 3 sulfonyl products. So, and finally, I would have summarized this, some of my works using the different reaction conditions. So using the organosulfur compounds, like, so other sulfur compounds we have been used, that is thiosulfonates. Here is the results were summarized. I hope you are able to see. So using this thiosulfonate, we are able to publish many papers. So other part of our research activities. So we could able to synthesize various organosulfur compounds. You can see here using the simple one molecule, one precursor, that is thiosulfonates. And as you know, during the Corona crisis, lockdown, we utilized it efficiently at times to prepare the review articles. We published a couple of review articles here. One is the RSA Advanced, another one is the Organic Biomolecular Chemistry. So among them, so this is the one RIC Advanced becoming the most popular 2021 articles that are recognized by the editorial board. And finally, acknowledgement of the, so I must thank to the all my research grants is summarized here, including the SERB project and CSIR, EMR2 and UGC startup grant, and particularly my student having the woman scientist that also has some grants under the women scientist grants. And also I would like to acknowledge my students, so and contributed significantly for the various aspects of the organosulfur chemistry. So today's my talk given the beta iodovinyl sulfone, this Jagadish and Harita and Sharada contributed for the corresponding beta iodovinyl sulfones. And of course, subsequently, other people will be worked on the corresponding the thiosulfone, which I shown the summary of my presentation. And finally, I would like to thank all my students, so who contributed significantly, and also thank for the one and all for your patience and kind attention, and also for my invitation. If you have any questions, I will be happy.
Any questions from the participants? Participants, anyone wants to interact with the speaker? You unmute yourself and then yeah, if you know, if there are no questions, we'll end the session by thanking Dr. Raju. So we are very grateful to Dr. Raju Janapredi for his interesting and informative lecture on beta iodovinyl sulfones, a versatile building block in organic synthesis. So Raju, we are very grateful to you for sparing your precious time and then sharing your expertise and knowledge in this particular area with our participants, and especially explaining the versatility of the beta iodovinyl sulfone in preparing molecules such as beta ketosulfones, beta ketothiasulfones, and extending the work to the synthesis of biologically important heterocycles like sulfonyl benzopherones and sulfonyl pyrazolopyridines. So we thank you, Raju, and your final slide is so impressive that is consolidating your work, and it's very much impressed with this final slide and at the same time with your work also. So thank you, Raju, once again.
Thank you very much, madam. I would like to mention one more thing. Is a couple of days we are moving to 2022. I wish you all the participants and Professor Leelavati madam and Ashok sir and all the organizers wish you a very happy new year to all of you. Thank you, madam. Thank you very much for your invitation.
Subhash madam, invite you.
Okay. So thank you, Raju. So with this Raju's presentation, we have ended with the 2 invited lectures we have completed. As per the schedule, our next program is about the CYSA presentations, that is oral presentations for the Young Scientist Award. So we'll go ahead, schedule also shared with the participants. So we'll go ahead with that program and then followed by the abstracts presentation after that one. So then immediately we are going to start as per the schedule for the first presentation. Please start sharing. Raju, you stop the screen sharing.
Yeah, ma'am. Yeah. Close it, ma'am.
And then the first participant is requested to just 1 minute, and then sir. One more announcement to the participants is for this session, which is going to start from now onwards, that will be chaired by Dr. Subhashini, that is organic chemistry. She is organic chemistry assistant professor from the Osmania University Department of Chemistry. with very good research background, produced almost about 10 PhDs and published many papers in reputed journals. And so this session will be chaired by Dr. Subhashini. So we welcome Dr. Subhashini.
Okay, thank you very much, madam.
The first participant, as per the schedule, is requested to share the screen with her presentation.
Okay. Okay, I'll read out the name of the first participant, Anu Chowdhury. Satyapal, title, Comparison of the Physico-Chemical and Catalytic Properties of Cobalt and Titanium-based magnetic layered double hydroxides in oxidative aromatization of 1,4-DHPs and oxidative deprotection of oximes. 8 minutes for your presentation, 2 minutes for question and answers. You are ready? Anu Chowdhury, you are ready? Sir? 1497. Maybe first participant is not available. May I call upon second participant, D. Ravinder. D. Ravinder, are you ready?
Yes, madam, I am ready.
You are available?
Yes, madam.
Okay. Title of this topic is In Silico Screening of COVID-19 and Synthesis of 6,1,4-aminophenyl 1H1,2,3 Triazole 4-aryl methoxy substituted benzofuran to aryl methanones using green synthetic protocols towards screening of their in vitro anti-cancer, antimicrobial activities. Okay. Now, Ravinder, you can take and you can start your presentation.
Okay, madam. Thank you.
The time is 8 minutes.
Good afternoon, all. I am Ravinder Dharawat, research scholar from Osmania University. Am I audible, madam? Hello.
Yes, you are audible. Yes, continue.
Yes. And my title is In Silico Screening of COVID-19 and Synthesis of 4-phenyl 1,2,3 triazole based benzofuran derivatives by using green synthetic protocols towards screening their in vitro anti-cancer antimicrobial studies. So benzofuran heterocyclic compounds are dominant backups for their biological and pharmaceutical activities. Among the heterocyclic compounds, benzofuran compounds are most important scaffolds due to their remarkable applications in biology as well as pharmaceutical and industrial applications like antibacterial, antifungal, antiprotozoal, antioxidant, etc. In present era of heterocyclic chemistry, 1,2,3 triazole is a privileged N-fused heterocyclic compounds in the medicinal chemistry. That named reaction is probably called click reaction. It is the reaction between alkyl group and aryl azide group. So here we started with the 2,4 dihydroxy aryl carbonyl compound, which is treated with propargyl bromide in DMF or dry acetone solvent by taking anhydrous K2CO3 as a base. We get the mixture of compounds. In that 2-hydroxy 4-propyloxy aryl carbonyl compound is a major one, and 2,4 dipropyloxy aryl carbonyl compound is a minor one. So we took this 4-propyloxy aryl carbonyl compound and synthesized the final derivatives 4 aryl 1,2,3-triazole benzofuran derivatives. We synthesized it in two different pathways. In pathway 1 or route 1, the intermediate 2 we treated with various types of aryl azide by means of click reaction condition, and we formed the intermediate 3 different types of intermediate, that is 4-amino phenyl 1,2,3-triazole based aryl carbonyl compounds. That intermediate further treated with various types of phenyl bromide in dry acetone as a solvent and K2CO3 as a base, and we finally found the target compounds. In the route 2, we were started with the intermediate 2A to C, and we are treated with different types of phenyl bromides in dry acetone solvent to get the 4-propyloxy benzofuran derivatives. That 4-propyloxy benzofuran derivatives further treated with various types of aryl amines, and those are performed with a click reaction, and we get the 4-aryl 1,2,3-triazole based benzofuran derivatives. Here we reported total 28 analogs. In that 18 are intermediate and 15 are final standard compounds. So in these two pathways, route 1 and route 2 is very convenient because the polarity difference between the intermediate 4 and final target compound 6. We have represented one of the final compound spectral data here. IR spectrum of the compound. The primary amine IR stretching frequency appears as a doublet at 3,478 and 3,377 centimeter inwards, and 2,922 as a CH stretching, 1,733 for the carbonyl stretching, and 1,264 for the ether linkage. Proton NMR of the one of the derivative. So here characteristic peak of the formation of triazole ring is triazole proton appears at as a singlet at 7.96 ppm, and methoxy OCH2 group appears as a singlet as 5.3 ppm, and methoxy group which is appears at 3.9 ppm as a singlet. Remaining protons appears in the aromatic region as a A2B2 pattern, and C13 NMR of compound. Here the characteristic peak is carbonyl compound which is appears at 182.4 ppm, and this methoxy group connected hypsocarbon appears at 163 ppm, and benzofuran attached carbon appears at 159 ppm, and this OCH2 linked hypsocarbon attached appears at 159 ppm, and this OCH2 carbon appears at 62 ppm, and methoxy appears at 55 ppm. And HRMS of the compound, exact mass of the compound is 440, and we obtain it as a 441 as a M+H peak. Among all the synthesized 15 compounds, we were interested to carry out their anti-cancer studies, and we performed in vitro anti-cancer study for all the synthesized compound in 3 cell lines, namely MCF7, PC3, and HeLa cell lines. By employing MTT assay, in vitro screening of these studies were taken in two different concentration, that is 5 micromolar and 10 micromolar. And finally, out of the 30 readings, we were concluded after incubation of 48 hours, we were concluded with 7 compounds out of 15 were exhibited good potent activities. Those 7 compounds results are we are compared with the standard compound doxorubicin, and those are illustrated in this table. So here doxorubicin was 3.14 plus or minus 0.42. So in this all the condition out of 15, 7 compounds are showing promising activities. So further we were performed the antimicrobial activity also, but I am not represented here. Those are also giving encouraging results. So in the present, we are as the antimicrobial as well as anti-cancer studies gives the good biological biological results, we were interested to compare this with the anti-COVID screening. That is molecular docking of anti-COVID screening. We know that coronavirus is a pandemic disease which is arisen in Wuhan, China, and superly spread throughout the world within the 6 months. And even today, we are suffering with the COVID-19 pandemic, and many experts are suggesting that we are going to face the third wave soon. So, because of this pandemic only, the human lifestyle is changed very well, and because of this caring only, we are presenting this in the virtual mode. So here our interest is we were taking the SARS-CoV-2 protease enzyme, and we were docked with the different proteins and enzymes, and finally we got these results that out of 15 derivatives, 2 derivatives are totally inactive, and remaining 13 derivatives are giving good hydrogen bonding interactions as well as hydrophobic interaction. And we are expecting to enlarge these studies further. And finally, I conclude, in this work, we successfully synthesized 4-aminophenyl 1,2,3-triazole based benzopherones, that is in the name 15 derivatives in 2 different pathways. And also we synthesized the compounds in the conventional method and sustainable microwave method. However, in microwave methods, we are getting the products in higher in the yield and with respect to lesser in the time also. And we performed the in vitro anti-cancer studies and antibacterial studies by comparing their results with the standard compounds like doxorubicin, ciprofloxacin, as well as fluconazole for the fungal compounds. And finally, we collated these studies, biological activity studies with molecular docking studies, and we were performed anti-COVID screening of the docking studies, and we were turned out with a good results. Yes, madam. Finally, I will thankful to the Professor Leelavati Madam, Sectional President, Organic Chemistry, Department of Chemistry, Satavahana University, for organizing this conference, and all the council members of Indian Council of Chemistry at Department of Chemistry, Usmania University, and my sincere thanks to CSR funding of my research work. Thank you, madam.
Any questions from the audience? Okay. Next participant. Thank you, Ravinder.
Okay, ma'am.
Next participant, Deepika Gidkar.
Yes, ma'am, I am present.
Okay. Your topic title is Hydromagnesite Sheets crowned with cobalt ferrite magnetic nanoparticles facilitated heterogeneous approach for the synthesis of benzo imidazo 2,1-B thiazole scaffolds. Okay, Deepika, you can start.
Shall I start? Okay. Good afternoon, everyone. I am Deepika Gidkar from School of Chemical Sciences, Devi Helda Vishwavidyalaya, Indore. Today, I am going to present my research work entitled Hydromagnesite Sheet Crowned with Cobalt Ferrite Magnetic Nanoparticles, Facilitated Heterogeneous Approach for the Synthesis of Fused Benzimidazole thiazole scaffolds. These are the contents which I am going to cover during my presentation, starting from general introduction to fused benzimidazole thiazole. Aim of
1 minute on your video, please. You're on your video.
Okay, ma'am. Mama, I'm unable to.
There should not be any problem, Kada. Video.
Okay.
Video icon symbol is there. You just. Yes, it is on now.
Okay.
You go ahead with
These
your
are the
presentation.
contents. Okay, ma'am. These are the contents which I'm going to cover during my presentation, starting from general introduction to fused benzimidazole thiazole, aim of the work which I have done, followed by the preparation and characterization of catalyst, reaction optimization, synthetic strategy, mechanism and its comparison with some reported methods, green evaluation, spectral analysis of synthesized compound, merits of our work, and finally the conclusion. Fused benzimidazole thiazole is an important heterocyclic scaffold isolated either from the natural products or accessed by synthesis. It is the result of a fusion of aromatic compound like fused benzimidazole to the 4th and 5th position of a pyrrole ring. As fusion with pyrrole ring enhances the delocalization of electron, which further enhances its property to a greater extent. Fused benzimidazothiazole and its derivative find their multiple uses in medicinal chemistry due to their broad spectrum pharmacological activities such as anti-tumor, anti-cancer, antimicrobial, etc. This slide shows some commonly used drugs like levamisole, quizartinib has been shown which are used as anti-inflammatory, anti-cancer, and PET analysis of Alzheimer's disease. In addition to drugs, these are also used as organic light-emitting diode, as herbicides, and optical brightening agents in detergents. The aim of our work is to design and develop a green strategy for the synthesis of fused benzimidazothiazole derivative from easily accessible and economical reagents. We have synthesized the hydromagnesite sheet crowned with cobalt ferrite magnetic nanoparticles using chemical co-precipitation method. Firstly, we synthesized the hydromagnesite sheet by the vigorous stirring of sodium carbonate and magnesium nitrate solution at room temperature. Then the obtained white precipitate of HMS was treated with aqueous solution of cobalt chloride, ferric chloride, and sodium hydroxide at 100 degrees Celsius for 1 hour. Afterward, the obtained black precipitate was filtered and washed with mixture of water and ethanol until the pH reached 7 and dried under vacuum at 60 degrees Celsius for 24 hours. After the preparation of the catalyst, we characterize it with number of techniques. The FSM and HR time images shows the size less than 50 nanometer and having good surface area. The EDS spectra presented here ascertain the presence of cobalt, iron, oxygen, magnesium, and carbon as the only element present in the composite. Here, the extra diffraction pattern help in calculating the crystalline size, which is found to be 12.30, 16.97, and 14.78 nanometer for the composite cobalt ferrite and HMS respectively. And the presence of the bit corresponding to HMS and cobalt ferrite magnetic nanoparticles on the diffraction pattern of composites indicates the successful formation of corresponding hybrid material. In FDIR pattern, the bends are attributed to the stretching and bending vibration of CH, CO, and OH group, and the bend at around 588 centimeter inverse is corresponding to intrinsic stretching vibration of metal at the tetrahedral site between iron and oxygen, and the bend at around 493 centimeter inverse is assigned to octahedral metal stretching between cobalt and oxygen. The intensity ratios are calculated from the Raman spectra for the composite and cobalt ferrite are 0.7965 and 0.7943 respectively. As we can see that it increases after doping of HMS with cobalt ferrite magnetic nanoparticle as expected. The magnetic hysteresis curve reveals a decrement in the magnetic saturation value for the composite as compared to bare cobalt ferrite magnetic nanoparticles. This decrement may be due to the spin canting at the surface of ferrite nanoparticles, and both the sample exhibit ferromagnetic behavior at room temperature. The sample exhibit mesoporosity with a pore volume of around 0.1020 cm3 per gram, and the specific surface area of synthesized catalyst is found to be 75 meter square per gram, which was determined by BT adsorption-desorption studies. Keeping the economic and environmental issues under consideration, we check the reusability of the catalyst and solvent for this protocol. And it could be seen from the graph that the recovered catalyst and solvent catalyze the reaction in acceptable percentage yields. And the yields of the product suggest no significant decrease in their catalytic activity and reaction efficiency. To synthesize this industrially important moiety, we need to monitor reaction progress with different amount of catalyst loading and optimize appropriate solvent, materials, and energy sources to minimize the cost and with save our time and environment. We optimize the reaction using various protic and aprotic solvent at different time intervals with varied amount of catalyst loading and found that we get excellent yield, that is 93% in PEG 400 as a solvent in the presence of 5 mole % of catalyst as shown in entry 11. This is our synthetic scheme in which a mixture of 2-amino-benzthiazole aryl benzaldehyde derivative, phenylacetylene derivative, and a catalytic amount of hydromagnesite sheet crowned with cobalt ferrite magnetic nanoparticles in PG 400 at room temperature for the ambient time, that is 15 to 30 minutes, leads to the formation of fused benzimidazothiazole derivatives. This domino reaction initiates with the condensation between 2-ABT and aryl benzaldehyde derivative, followed by dehydration, which leads to the formation of shift space A. The A3 coupling strategy, where the basic sites of HMS promotes the formation of cobalt ferrite acetylide complex by the activation of proton from phenylacetylene, and the cobalt ferrite acetylide attacks on the preformed iminium ion A to form intermediate B. The later undergo 5-exodecyclization step by an attack on the alkaline unit by benzthiazole nitrogen, which resulted in the formation of our expected compound. A comparative account of literature protocol for the synthesis of desired derivative and our present work is shown in this table. As compared to the reported method, our present strategy offers certain advantages such as high product yield, simple procedure with easy workup, along with the reusability of the catalyst and solvent, leading to the efficient synthesis of our desired product. Today, we all are facing health-related problems due to environmental pollution, and we can't simply blame to the automobiles and industry for polluting the environment. Rather, we, the researchers from laboratories, are found to be the major source for polluting the environment in the name of research and progress. So it's our duty to incorporate such protocol which minimizes the pollution and which save our time and environment. In this regard, we calculate the eco-scale parameter and found a score of 78, which is indicative of an excellent synthesis. Characterization of synthesized compound with number of techniques. This slide shows the FT-higher spectra in set pick table along with their corresponding bonds. This is the 1H NMR spectra for the same. The merits of our protocol are synthesis of diversified fused benzimidazothiazole derivative, recyclable heterogeneous catalyst and solvent, low catalyst loading, comparatively mild reaction condition, low E factor, high yield of the product up to 94%, acceptable eco-scale value of 78, and atomic economy that is 93.36%. Finally, I would like to conclude my work by saying that we have developed a simple, rapid, and sustainable protocol for the synthesis of fused benzimidazothiazole derivatives using efficient nanocatalyzed material and high efficiency, eco-friendly behavior, excellent reusability of the catalyst and solvent, and obeying 3R concept put this protocol under the umbrella of green chemistry. Firstly, I would like to acknowledge my guide, Dr. Pratibha Sharma ma'am, and Head School of Chemical Sciences, DAVV Indore, and last but not the least, IIC, for giving me this platform. Some of my achievements. This is our list of publications. Thank you.
This work is published.
Ma'am, only the catalyst part is published in RSC Advances.
Only catalyst work is published. Other things not yet published. Huh?
No, ma'am.
Okay. Okay. Any questions from the audience? Okay. Thank you, Deepika.
Okay. Thank you so much, ma'am.
We'll go to the next participant.
Yes, ma'am. Go over them.
First person is available, sir. Okay. Anu Chaudhary. Anu Chaudhary is available. First, later. Okay. Govardhan Lanka.
Yes, ma'am. Yes, ma'am. I'm available.
You're available. Okay.
Yeah, ma'am.
Your title is Structure-Based Hierarchical Virtual Screening of Antiviral Libraries for the Discovery of New Molecular Entities as SARS-CoV-2 Main Protease Inhibitors.
Yes, ma'am.
Okay, you can start.
Yes, ma'am. Myself, Dr. L. Govardhan, Research Associate, DBT, Department of Pharmacy Bits Planning. Currently, I'm working under Program Ghosh.
On your video, Govardhan.
Yes, ma'am.
Participants are requested to on their video during presentation. Govardhan.
Yes, ma'am.
Okay, go ahead. In between, I think you went for mute.
Yes, ma'am. Myself, Dr. L. Govardhan, Research Associate, DBT, currently working under Professor Balram Ghosh. Good afternoon, everyone. So, I'm going to present oral presentation of ICC 2021, which titled Structure-Based Hierarchical Virtual Screening of Antiviral Libraries for the Discovery of New Molecular Entities as SARS-CoV-2 Main Protease Inhibitors. Novel coronavirus disease, which is abbreviated as COVID-19, which found in December 2019, which caused by new strain of new virus family called SARS-CoV-2, which ultimately led to the worldwide pandemic. The common symptoms associated with this disease is fever, dry cough, cold, loss of taste and smell, headache, runny nose, sore throat, and fatigue. The main idea behind in identification of new therapeutic strategies, novel therapeutic strategies, novel drugs, are the lack of effective drugs for the main protease enzyme for this, especially for this new strain of virus, and inefficacy and cost related issues with the repurposed drugs and FDA approved drugs. which are the key factors which are motivated us to identify novel therapeutic strategies against main protease of SARS-CoV-2. Here, main protease enzyme, which is a non-structural protein of SARS-CoV-2 enzyme, which is recognized in this work as an attractive drug target, which synthesize with manufactures the structural proteins called spike, envelope, membrane, nucleocapsid, which are part of the SARS-CoV-2 structure, which are plays key role in viral replication and transcription. Therefore, we target the SARS-CoV-2 main protease enzyme for the identification of novel drug candidates. So, present work considers the main protease enzyme as a novel attractive drug target for the discovery of new chemical entities. So, this is the biochemical pathway of main protease of SARS-CoV-2. This is the structure of SARS-CoV-2, which is a spike protein. Spike protein is a key important structural protein, which also consists of an envelope and nucleocapsid with RNA, which plays key role in viral replication. Main protease is a non-structural protein which manufactures these non-structural proteins: spike, envelope, membrane, nucleocapsid. Spike is an important structural protein which makes the protein receptor complex with the ACE2 receptor in lungs, which allows viral entry into the body host cell, in turn causing viral replication and transcription, which leading to the virus load, and in turn causing the COVID-19 infection in the lungs. So this is the retrieval of crystal structure of main protease of SARS-CoV-2. We retrieved the crystal structure of main protease enzyme with PDB ID 6LU7 from RCSB PDB protein data bank, which is first published crystal structure. In the residue interactions with the crystal structure of main protease enzyme is we retrieved with the reported inhibitor called N3. The residue interactions of N3 ligand with this main protease enzyme are used to carry out the docking studies to identify new molecular entities using various small molecular libraries. So this is the link plot diagram of N3 inhibitor, which is reported with the main protease enzyme 6LUC1 PDB ID. So these are the residue interactions with which are active site residues. These particular active site residues, which are used to conduct grid generation, to generate grid generation, which incorporated into the further docking studies. Our main aim is to identify better lead molecules by identifying the some new novel pharmacophore scaffolds, which may be act as active scaffolds or active molecular entities in designing new molecular entities, which may be act as potential inhibitors against main protease in further synthetic development. So we have conducted structure-based vulture skinning using GLIDE module of Schrödinger suit. We have taken a total of 15,400 antiviral compounds from various diverse molecular databases from ChemDiv, Enamine, and coronavirus library. We have conducted a ligand preparation for the generation of minimized coordinates, which have resulted in 79,800, which are minimized coordinates. So these output ligands, which are further subjected to the docking studies using Schrödinger suit in a sequential filtrations called high throughput virtual screening, standard precision, and extra precision docking modes. So finally, it resulted in 38 hit molecules. 38 final hit molecules. From 38 hit molecules, we have prioritized. We have scored the potency of the lead molecules. We have prioritized a total of 6 lead molecules. Their potency prioritized and ranked according to the scoring functions called docking score and glide energy. And we have also carried out some binding free energy studies to estimate the binding energy between ligand molecules and receptor main protease that are prime MNGBSA from Schrödinger suit, and also we have conducted autodock. We have used these both procedures to conclude that both procedures will producing the same results. Same molecules will become act as potential inhibitors against main protease enzyme. These are the residue interactions. Then optimization of leads. From among these 6 lead molecules, we have optimized 3 lead molecules, M1, M3, M6, as better lead molecules. These are the best docked molecules against main protease enzyme, which have circled with the red color, which have circled the scaffolds. Maybe these are the pharmacophore moieties interacting with the interacting with the main protease receptor. So maybe these pharmacophore these new scaffolds maybe act as active scaffolds in designing potential inhibitors and designing new drug candidates against main protease enzyme. So these particularly these 3 molecules among those 6 lead molecules are showing good glide score, docking scores, and lowest negative delta G binding free energy values, and also binding free energy from autodock. And also these 3 molecules exceptionally showing the maximum percent human oral absorption against maximum percent human oral absorption, that is 100%, and M6 is showing almost highest percent human oral absorption, which we in turn call which we expressed in terms of bioavailability, that is 93.23. These are the 3D binding interactions and how they are how these 3 lead molecules are interacting with the main protease enzyme and their binding poses. These are the 2D ligand interaction diagrams of the final lead molecules. Finally, ADME properties, pharmacokinetic properties. Pharmacokinetic properties of all the 6 lead molecules are falling in the range of acceptable ranges, which I have shown below. All are following the Lipinski rule of 5 and RO3, RO5, Jorgensen rule of 3. And also, particularly these 3 molecules are showing very high maximum bioavailability, that is percent human oral absorption, 100, 193.23. And we have also carried out some comparative docking study of FDA with FDA approved drugs, which are using to treat COVID-19 infection as a immediate usage. The FDA already existing antivirals. So these are the existing antiviral drugs which are approved by FDA, and we have conducted a comparative docking study using these FDA existing drugs. These newly identified lead molecules from the virtual screening studies M1, M3, M6 compared to these existing drugs, antivirals, these newly identified lead molecules are showing better glide scores and glide energy, and also showing some, except remdesivir. Remdesivir is showing some good scores. Okay, madam. These 3 lead molecules are showing exceptionally very good docking scores and human parcel. These are the key findings in conclusion. We have conducted a structure-based virtual screening, which resulted in 38 compounds, prioritized 6 lead molecules based on scoring functions, docking score and glide energy. From the 6 lead molecules, 3 lead molecules we have optimized using binding free energies and autodock binding free energy values. These 3 lead molecules, the same lead molecules found to show high percent human oral absorption values, and also they are consistently binding to the active site key residues of main protease enzyme, that indicating the selectivity of their binding. Also comparative study also proving that the new lead molecules identified from the virtual screening studies may act as better lead molecules in the treatment of COVID-19 infection. Acknowledgements. I would like to thank Head Nizam College and Principal for providing research facilities for carrying this present work, Usman University, and I'm thankful to my supervisor, Dr. Satavahana, for guidance. I would like to thank Professor Balram Ghosh for his support and guidance. I would like to acknowledge the DBT, Government India, for the financial assistance as RA2 under the DBT project. Thank you, ma'am.
Okay. Next.
Yes, ma'am.
Okay. Shalini Sharma is available. Shalini Sharma is available. If she is not available, we'll call upon Sandhya Jonnala.
Yes, ma'am, I'm available, ma'am. Sandhya Jonnala.
Okay. So your title is Stereoselective Total Synthesis of Thiacillomycin E. Okay.
Yes, ma'am. Yes, ma'am.
You can start.
Yes, ma'am. Ma'am, unable to share the screen. Okay.
Govardhan, you are able to share?
Yes, ma'am. Now I'm able to share.
Okay, okay. Switch on your video also. Yes.
Am I audible, ma'am?
Yes.
Good afternoon, all. First, I would like to thank to ICC Indian Council of Chemistry, Satavahana University for conducting this prestigious conference, and also thanks to Professor P. Leelavati ma'am, sectional president, also Ashok sir, and also I would like to thanks to organizer of this program, Sarasija madam, and coordinator Namrata madam, and also I'd like to thank to Subhashini madam for hosting this oral presentations. Myself, Dr. Jonnala Sandhya, I completed my PhD under the guidance of Dr. B.V. Subbareddy sir at IICT Hyderabad, Chief Scientist, IICT Hyderabad. Presently, I'm working as an associate professor in the Department of Chemistry, Vageshwari College of Engineering. Here I'm presenting my work. It is a total, a concessive stereoselective synthesis of stereoselective synthesis of pecillomycin E. Here, the objective of the work, prepare the fragments by using the retrosynthesis and Misno-based purification. And the scope of the work of this is different analog synthesizer and screen of their activity. Here, when we are just using the Misno-B reactions, it's used to help the, also it's used to retrosynthesis protocol. They are ring closing metathesis as the key steps. And this approach is successfully demonstrated as Alder-Rickert protocol for the construction of the retrocyclic acid lactones. And pecillomycin compounds fragments are also just named as an retrocyclic acid lactones. But the method we have to use to develop the pecillomycin E with the help of the retrosynthetic process and also using the Misno-B synthetic process, Alder-Rickert protocol. Then we developed the retrocyclic acid lactones are group of fungal polyketide metabolites that are structurally consist of C11 ring. Actually, it's having a C11, but when it is just ring closing, they are formed as a C14 member ring. And this C14 member ring, it shows the number of biological activities such as estrogenic, antifungal, cytotoxics, antimalarial, antiviral, antiparasitic, and numicidal behavior. And passionating of these all the biological activities, we developed a pecillomycin in in this synthetic process. And also, this pecillomycin shows the inhibitor activity against ATPase and kinases. Is a kinases is one of the enzyme, but it's a last 2 decades. The kinases enzyme is also related to the number of diseases. So, due to this consequence of inhibition of kinases, a development of new drugs is coming to the ears. And there are some pecillomycin fragments. Is a pecillomycin A, pecillomycin B, pecillomycin C, pecillomycin D. Pecillomycin E and F are the epimers, and they are having the same structure. They are the epimers. And here we just synthesize the pecillomycin E through the retrocyclic synthesis process. The structure of this natural product elucidated by the extensive NMR analysis, single crystal X-ray studies, and chemical correlations. Pecillomycins are found in exhibit antiplasmodial activity against plasmodium. And pecillomycin E was found to have a remarkable activity with an IC50 value 20.0 nanometers. Although there were several reports on the total synthesis of retrocyclic acid lactones, but to the best of our knowledge, there are two synthetic approaches we have to found to synthesize the total synthesis of pecillomycin E. And this is the retrocyclic analysis of pecillomycin E. And pecillomycin E, the fragment is just formed by the seven fragment. It is a aromatic acidic compound, and eight fragment is known as an aliphatic segment of the D ribose, and 7 fragment is synthesized from the is a diene. It means 9 fragment diene, and also it is synthesized from the 10th compound. It is a dibiphenyls and alkyne ester, and 8th compound synthesized from the 11. It's a pent-4-ene 2 phenols, and also it is the TBS ester. Then TBS ester, it is synthesized from the sorry ma'am. TBS is synthesized from the hydroxy ester of the D-ribose. The hydroxy is it's synthesized from the D-ribose. Then the fragment, the main key fragments are 7 and 8 compounds are the main key fragment. So firstly, before fragmentation synthesis of specilomycin, the 7 fragment synthesis is done by the 9th fragment and 10th fragments. It's diene and alkyne ester, they are involved in Alder-Rickert reaction. Or also this is the extension of the Diels-Alder reaction by using neat N-and dimethyl aniline, and this is the mechanism process is going on. It's done, and then it forms about TBS ester, and then here deproduction of the TBS ester in the presence of the osmium pyridine CS3CN, it forms an alcohol ester. Alcohol ester, it's a OH group, and then alcohol ester is again it's react with the catalytic hydrogenation. It's involved in Alder-Rickert reaction in the presence of Mishnobi process, triphenyl phosphates, imidazole, and it is just formed as an iodoform, and then again it is hydrolysis process takes place in the presence of lithium hydroxide, water, and methanol H2O. It's a reflux 7 hours and 92% of yield. The main key fragment 7, it is an aromatic acid we got. As per our strategy, specilomycin E was achieved by the Mishnobi esterification. Mishnobi esterification is mainly used for the conversion of the alcohols to esters. So, and ring closing metathesis process is very helpful in this process. The fragment 7 is synthesized by the alkyne ester 10 and dienes 10, and it is Alder-Rickert reaction. The 2,5-dimethoxy-9 is treating with an N-and dimethyl 180 degrees centigrade and 48 hours, sealed in the 56% of yield is there, and the fragments 9 and 10, they are developed in commercially available 3-butylene 1-ol and through the Alders-Rickert reaction. And one more fragment is like an olefin ester. It is also one of the key fragments to develop the specilomycin E. It's a key fragment 12. It is an ester of this is from the D-ribose, and it is a simple reagent we have to use. That is a Witting reagent is used to form the ester of this compound, and then under the Mishnobi conditions like pyridine, triphenyl paspin imidazole, then it forms its like TBS ester, alcoholin ester, and then it is TBS chloride imidazole. We get the 12. It is an TBS ester. Next, we attempted the aliphatic segment of, and this 12 is aliphatic segment of the D-ribose. According to D-ribose converted to the hydroxy ester, and primary alcohol 14 was converted into isoderivative using iodine, triphenyl paspin imidazole, with then treated with the, again it's treated with the zinc and sodium iodide reflexing ethanol to offer hydroxyl olefin. 80% of field we got, and protection of alcohol 18 is using with the help of TB as a tertiary butyl sulfonyl chloride and imidazole DMF gave the TBS is 12 is not 12. It means the aliphatic fragment segment of the D-ribose with a 92% of yield. And one more key fragment to develop the specilomycin E is the fragment 8. Is fragment 8 is developed by the fragment 12 and fragment 11. When here we are used Hubidiono groups grade 2 generation 2 catalyst, and this catalyst is especially used to for the cyclization process according to the Mishnobi reaction, and the grade 1 of this reagent is not helpful for, and while you have to use the grade 1 of this reagent, it is for a dimer formation, but here Hubio grubs 2 generation we just use, so it is converts to alkenes. Again, alkenes in the presence of the nickel and ethyl alcohol, then it's a catalytic hydrogenation takes place. Then it forms as an ester. Then it's involved in the process as a reduction process with in the presence of the dibyl H and chlorides, and also triphenyl phosphates, N-butyl lithium, and 78 degrees of centigrade temperature. 1 hour is a overnight sleep, and it forms an ester formation. 21 is a fragment. Then the 21 fragment is again it's involved in the reactions in the presence of DDQ, dicyanodichloroquinoline, and under the conditions of the hydrolysis, then it forms in a fragment 8. It is an alcoholic fragment, and this fragment is one of the key point for the formation of the specilomycin E as well. 7 fragment. So alcoholic group of 8 fragment and acid group of 7 fragment, they are the very key point for the formation of the specilomycin E. Another key fragment, it could be achieved by the olefin cross metathesis of the 11 and 12. Then the compound 12 will be synthesized from the compound 14, which in turns could be prepared from commercially available D-ribose. The cross metathesis reaction between pent-4-ene 2-ol derivative, it's like a 7 fragment and alkene using Grubbs second generation catalyst. As I mentioned just now, Grubbs second generation catalyst is helps to avoid the formation of the dimer, and also it helps for the cyclization process. And so during this process, in reflexing of CS2Cl give the alkene is a 19 fragment is a 72% of yield. Then catalytic hydrogenation of alkene, and in the presence of the Ronnie nickel, its atmospheric ETOH is added, is a 20, fragment 20 is an ester, it is a 92% of yield we got, and reduction of ethyl ester 20 using dival is a minus 78 degrees Celsius offered corresponding aldehydes, which was immediately treated with chlorine. C1 Witting yield. The Witting reagent is also helps in the process. It's a common general procedure, non-procedure method, but C1 Witting reagent is terminal olefin. It forms with the 81% of yield. Oxidative removal of PMB takes place from the 21 fragment to an 8 fragment. When it is 21 fragment, it's an ester. It's involved in oxidative removal process by the removal of PMB, paramethoxybenzoate, and in the presence of the dichloroquinoline, give the aliphatic segment of D-ribose, that is the 8th fragment we got. And finally, as a completion of the total synthesis of pecilomycin, the key fragments like aromatic acids like a 7th fragment, and
Andhya, you conclude, ma.
Yes, ma'am. It's just 1 minute, ma'am. Aliphatic segment of the D-ribose is there involved in the Mishnobby reactions. Then ring cyclization process takes place. Then after 22 fragment, after the ring cyclization, it's again involved in the Grubbs second generation catalyst we can use. Then it's converts to total ring formation of the ester. Then again, global deproduction process, either by the global deproduction with the help of BCl3CS2Cl. Then finally we get the pecilomycin E. The global deproduction means that we have to deblocking the production of the side chains. So throughout this, all the steps involved in the synthesis of pecilomycin E, it's a retrocyclic, means the process every fragment we synthesized by just getting the pecilomycin E. Then I just to conclude this, having a sufficient quantity of 7, it means aromatic acid and aliphatic segment of the D-ribose is a very essential key points for the production of the pecilomycin E. And the last final key step is global production of the macrolactone 23 were achieving used in at room temperature. Offered a targeted molecule pecilomycin E, it's having a lot of biological activities. And in conclusion, we have demonstrated an efficient synthetic approach for the synthesis of pecilomycin E, starting from easily accessible precursors. As a starting material, we just choose it here. It is an easily available in the market, like a commercially available in the market, that is a para-hydroxyparagryl. The key steps involved in this synthesis are Alder-Rickert reaction. Alder-Rickert reaction is an extension of the Diels-Alder. This is very helpful in this process. Mishnobby esterification, because all the alcohol here in converts to the ester and they are in the process. RCM, ring closing metathesis reaction. This approach is modular for the synthesis of other structurally similar natural products and their analogs. Then they are my list of publications. Total, I have 10 publications in reputed journals, Scopus and elsewhere, and also Bentham Science. And around 15 conferences, international and national conferences. And and this is my achievement. When I finished my PhD in 2020, immediately I got a very opportunity that I was selected as an associate fellow in Andhra Pradesh Academy of Sciences, like APAS 2020. And finally, I acknowledged Dr. B.V. Subbareddy Garu is the Chief Scientist, ICT Hyderabad, my guide, and he helped to complete my PhD. And Dr. G. Srinivas Reddy Garu, where I'm working here, Vageshwari College of Engineering, is for supporting for continuous research work. And Professor M.V. Basveshwar Rao, sir, Honorary Secretary of APAS Amaravati, and Ramesh Gardas, sir, and only the person.
Okay.
Thank you, ma'am.
Okay.
Thank you so much.
Is this work published?
Yes, ma'am, it was published.
Published work you are presenting?
It's recently published, ma'am.
Recently published. Okay. Okay.
Thank you, ma'am.
Right. Next. Next one, Yan Goda. Neha Goda is available. Suresh C. Neha Goda. Anybody is there?
Yes, ma'am.
Yes?
Just wait for 2 minutes.
Neha Goda is there?
Yes, ma'am. Neha Godha is here.
Yes. Okay. Neha Goda, you can present your work. Your title is text screen sharing. Use of some metal ferrites as a catalyst in aldol reaction.
Yes, ma'am.
Okay, you can start.
Yeah, just 2 minutes, ma'am. Ma'am, can you visible my slides? Hello? 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 Ma'am, can you visible my slides?
Neha, slides are not visible.
Now it is visible. Now it is audible.
Ma'am, you are audible, but can you visible my slides screen?
Neha, slides are not visible.
Okay.
What happened? Neha?
Ma'am, just give me a 4 minutes actually. Why it is not visible, I don't know.
Screen sharing.
Ma'am, I'm joining from my mobile actually. So,
Share screen is available, no? From there you can.
yeah, ma'am, but I.
అమ్మాయికి స్క్రీన్ షేరింగ్ చేయడం రావట్లేదు.
Ma'am, can I present after half an hour, please?
Share content, share screen, have you clicked?
Yeah, ma'am, I can share, but why it is not visible, I don't know.
Have you done that?
Yeah, ma'am.
Share screen?
Yes, ma'am.
సెల్ పని చేసలేని మీ దగ్గరకు వచ్చేసినాను. Neha? Neha, are you available? Neha?
Yes, ma'am.
Can you send to this mail, sectional president?
Okay.
We'll start. We'll operate from here.
Ma'am, kindly give me 12 to 15 minutes. Actually, I will join presentation.
Actually, madam, can you leave and join once? Maybe you can try that way.
Yeah, ma'am. Actually, I will
Leave
do
and
that.
join again, probably.
She left. PPT పంపిందా వాళ్ళు? Okay, maybe some problem is there. So we'll start oral presentations. So first, G. Prabhakar. G. Prabhakar is there? Oral presentations will start. We'll give time to Neha Goda. First candidate, G. Prabhakar. Is available? All the oral presentations be ready. We'll start oral presentations. Then next, third one is Navanita Gowda. Navanita Gowda is there, available? Oral presentations, whoever is available, please respond.
Ma'am, I, Shweta Poddar, is available right now.
Shweta
Poddar.
Poddar. Can you tell your number? Okay, 11.
Yes, ma'am.
Okay, 11. You start
Yes,
your work. Okay.
Okay, ma'am. Okay. Thank you very much, ma'am. Ma'am, is my screen visible?
Yes. Yes, right.
Hello, madam.
Slide shows.
Yes, screen is visible.
Yes,
Go on,
ma'am.
yes.
Okay. A very good afternoon to everyone. My name is Shweta, and the title of my work is Catalytic Effect of Phosphotungstic Acid, Functionalized Fe3O4, Magnetic Nanoparticles blended with TiO2 for synthesizing novel spiroacridines and evaluation of their medicinal potential on the receptor sites of the main protease SARS-CoV-2. This is the table of content, starting with the introductory part. As we all know, spiroheterocycles. Spiroheterocycles are those compounds which have at least two molecular rings connected with one single carbon atom. So owing to their structural rigidity, structural complexities, and unique pharmaceutical properties, they implicate an interesting challenge to many of the researchers and lead to the relevant drug discoveries. Furthermore, the exploration of appropriate catalysts are being used nowadays to enhance the rate of the reaction, also to increase the productivity of the synthesized drugs. Also, computer-aided drug designing such as TDDFT, molecular docking studies, QSAR technologies have become indispensable to design and develop newer moieties. Work is to formulate novel synthetic approaches to ascertain the structures of the synthesized novel moieties as well as the catalyst by different spectroanalytical techniques such as 1H NMR, 13C NMR, X-ray crystallographic studies, and many more, and to evaluate the medicinal potential of synthesized heterocycles. The main or the unique captivative features of my work is first, the use of ultrasonic irradiations. The reaction was augmented with the help of the catalyst, that is Fe3O prepared catalyst, that is Fe3O4 blended with TiO2 and phosphotungstic acid in PG green solvent. The reaction was effectively the three-component multi-component synthesis was done. Smaller E factor, mass intensity, short reaction time, high atomic economy, suffixes with the green chemistry approach. The catalyst and the solvent were easily recovered, and the recyclability was done. Also, the potential sites of the synthesized moiety with the receptor sites of the main protease SARS-CoV-2 were identified through molecular docking studies. This slide represents the experimental part of the catalyst preparation. The catalyst was prepared in 3 different stages. First, the co-precipitation method was followed, which then was followed by vapor thermal method, and then lastly, Fe3O4 blended with TiO2 along with phosphotungstic acid was prepared. This slide represents the characterization of the catalyst. Figures A1 and A2 represent the XRD patterns. Figure B represents the EDX spectra. C represents the FTIR spectra, and figure D represents the scanning electron microscopic images. The overall morphology of the catalyst so obtained was spherical in shape, and the average crystallite size was obtained was about 24.36 nanometer, and this was calculated by the help of Scherer formula. This slide represents the synthesis of the novel series of spiroacridine moieties. The mixture was sonicated in ultrasonic processor having 30 watt power and frequency 20 kilohertz. The reactants which were used were dimidone, substituted aniline, spin join. The reaction was completed within 10 to 14 minutes, and the temperature of the reaction was 70 degrees centigrade. This slide shows, the figure second shows the number of protons and the type of protons present in the synthesized moiety, while figure 1 represents the peaks associated with that. This slide shows the 13C NMR and mass spectrum of the synthesized moiety. The plausible or the believable mechanism was followed by Neuville condensation along with the Michael addition, and with the removal of water molecule, the product was formed. The reaction were also optimized. Table 1 represents the synthesis of various spiroacridines, and it was found that electron releasing groups reacted much faster as compared to the electron withdrawing groups. Use of different solvent at different temperature were also done, and the best result was obtained when the solvent used was Pg200 and the temperature was 70 degrees centigrade, and the reaction was completed within 10 to 14 minutes with a yield of 94 to 96%. These graphs represent the reusability and the recyclability of the catalyst as well as the solvent. Furthermore, to explore the medicinal potential of the synthesized spiroactidine, the docking simulations were carried out using the autodock vena, and the protein which was used was PDB ID6LU7. This is the main protease, main coronavirus protease, which plays a vital role in processing of the polyproteins. The mean value of the docking score so obtained was -8.23 kilocalorie per mole, and this is very close to that of obtained by most of the well-known antiviral reagents. This slide represents the 2D and the 3D interaction between the protein, that is the protease viral protein, and the ligand, that is the spiroactidine. Thus, I conclude that a new series of spiroactidine derivatives were formed, which was diluted in short reaction time with appreciable amount of yield. The methodology fixes with the green chemistry approach. The reusability and the recyclability of the catalyst and the solvent remain unaltered after the several runs. Also, the molecular docking studies were performed to evaluate the medicinal potential of the synthesized moiety. Acknowledgement. I am very thankful to my supervisor, Professor Ashok Kumar sir, Head School of Chemical Sciences, also Director, Devi University, Indore. SAP UGC New Delhi Research Grant for providing funding and SIC facilities, UGC DAE CSR Indore. Also Director SAP Chandigarh for their support in providing all characterization facilities. And last but not the least, the ICC Hyderabad team for letting me this platform to represent myself. Thank you.
Hello, madam.
Okay, thank you.
Hello,
Next,
madam, number 3, Navneet Gowda is available, madam.
Okay. Before that, Neha Goza, if she is ready, we'll continue that presentation. Neha Goda. Neha Goza, you are ready? Neha? Neha Goda, ఇక్కడ కనపడుతుందిగా అదే సార్. Neha Goda is there? Neha, you can start your presentation. Time I will 3:53. Neha, are you available? You're not audible.
Hello, can you audible, ma'am?
Yes, yes,
okay.
Right.
Yeah,
you can start.
Okay, good afternoon to all my respected professors and friends. I'm Neha Goda from Pacific University, Udaipur, Rajasthan. My supervisor is Professor Suresh Mehta, sir. First of all, thank you for giving me this opportunity to introduce my work, that is use of some metal ferrites as catalyst in aldol reactions. Metal ferrites, oxides of iron with other metals, are called metal ferrites. These ferrites have electrical as well as magnetic properties. General formula for ferrite is MFe2O4, where M is divalent such as Zn2+, Cu2+, Nickel2+, CO2+, etc. Synthesis of nanoparticles. Hydrothermal processes are used for synthesis of nanoparticles. In this process, we used copper nitrate hexahydrated and iron nitrate nanohydrated as a precursor with NaOH. Copper and iron nitrates are dissolved in distilled water by maintaining the ratio of nitrates and water as 1:3. The resultant solution is stirred and NaOH is added slowly into the solution of maintained pH of 11 to get pure spinel phases. Mixture is stirred, then it is transferred into a Teflon lined steel autoclave for 48 hours at 150 degrees Celsius temperature. And after heating, the autoclave was cooled at room temperature. It is washed several times by distilled water and then with acetone till the pH reaches 7. Now ferrites are separated from the autoclave and dried it around 60 degrees Celsius for 6 hours. And as prepared powder of copper ferrite is characterized by FeSEm, EDS, XRD, etc. The XRD data show that copper ferrite is in a crystalline phase. The particle size was calculated by Debye-Secher equation. It was found to be at 35 nanometer, which is given below in the graph. And the XRD data show that copper ferrite is in a crystalline phase. The particle size was calculated by Debye-Secher equation. And as there are only peaks for iron, copper, and oxygen, which indicates that copper ferrite is in a pure state, and they do not contain any impurity, which we look in the graphs like iron, copper, and oxygen, and no more impurities. And the morphology of copper ferrites in images which show that which show the shape of ferrites like square shapes and road-like structure. That is the only one indicate that the ferrites are is pure. And importance of aldol reaction. The aldol reactions has been used in large-scale production of the commodity chemical pentaerythritol and synthesis of the drug Lipitor for heart disease, that is atorvastatin calcium salt. It works as an intermediate for perfume production also, and it is also used in pharmaceutical industries, and it is used to prepare plasticizers. And now the aldol reactions. In this reaction, we follow some steps. That is, NaOH is dissolved in 25 ml of water, ethanol, which is 20 ml around. And now we add 0.9 ml of acetone and 2.5 ml of benzaldehyde, and then it will stirred about 30 minutes. Then we will found the yellow colors precipitate. It is filtered with the suction and washed thoroughly with the water to remove excess of alkali. Crude product was added to 50 to 100 ml ethyl acetate. Then magnesium sulfate was filtered, then solvent is removed with the rotatory evaporator. Product is crystallized in minimum amount around 5 ml of warm ethyl acetate. So yellow colored crystal are obtained on filtration by suctional. Then we will found it is a 36% yield, and the melting point around 100 degrees Celsius. But when in presence of copper ferrites as a catalyst in aldol reaction, we found that the yield is increase around 90%. So that is my work in presence of copper ferrites. Now, thank you for giving me attention. Thank you everyone.
Okay, thank you. Next one from oral presentations, number 3.
Navneet Gowda.
Yes, Navneet Gowda.
Yes, madam.
Your title is Synthesis of some novel Isatin thiazole conjugates and their computational and biological studies.
Yes, madam.
Okay.
Good afternoon, everyone. My name is Navneet Gowda. My title is Synthesis of novel Isatin thiazole conjugates and their computational and biological studies. Is the contents of work. Isatin is an encouraging class of biological active materials present in numerous plants and human tissues and bloods. Isatin derivatives are useful for the pathogenesis of peptic and gastric ulcer, known to exhibit broad spectrum of biological activities. Additionally, they have been also used as corrosion inhibitor, fluorescent sensor, and also applied in dye industries. Thiazole are the most important efforts in heterocyclic chemistry and important role in drug design. Hydrogen exhibits a wide range of biological activities and they also reported luminescent probes and molecular sensor. The current study aims to synthesize some novel acetylene linked thiazole hydrogens by one part multi-component reaction characterized by various spectroscopic techniques such as UV, IR, NMR, and HRMS. The quantum chemical parameters were analyzed using DFT studies and evaluated their antimicrobacterial and anti-inflammatory activities. The present work is the mixture of acetylene, thiazamic carbazide, and 2-bromoacetylene derivatives are dissolved in 10 ml of ethanol using 2 drops of acetic acid. The resulting reaction mixture was stirred with reflex at 60 to 80 degrees Celsius for about 2 to 3 hours. The progress of the reaction was monitored by TLC. The evaluation of their antimicrobial and anti-inflammatory activity. This is IR spectrum of one of the compound 4A. 3 to 119 switching frequency shows the NH peak, and 1694 shows the carbon C double bond O peak. This is the proton NMR spectrum of the compound 4A. This is the C13 NMR spectrum of the compound 4A. This is the HRMS spectrum of the compound 4A. The computational study, the global reactive parameters are calculated using synthesis compared by Gaussian 9 software. Here, among the synthetic compounds, 4H has a large energy gap and 4B has a small energy gap and acts as a good electrophile. This is the FMO orbitals of and HOMO-LUMO energy gap of the synthetic compounds. The biological applications: anti-tuberculous activity tested against Mycobacterium tuberculosis by an microplate Ulmer blue assay. In this, 4D and 4E shows a significant activity, and other shows other compounds shows a moderate activity. This is anti-microbacterial activity images of synthetic compound. The anti-inflammatory activity of the synthetic compounds are determined against MMP2 and MMP9. In this activity, the 4D exhibit a very good efficiency inhibited against MMP2 and MMP9. Remaining derivatives except 4F all shows a moderate activity against MMP2 and MMP9. Finally, I conclude my work. I have synthesized some novel acetylene thiazole conjugates, and the compounds were examined by different spectral analysis like FTR, NMR, C13, and HRMS. Some global and reactive parameters are calculated by using DFT studies. Further, the synthesized compounds are screened for antimicrobacterial activity and anti-inflammatory activity. The compound 4A and 4E exhibit significant antimicrobial activity. From anti-inflammatory activity against MMP2 and MMP9 results, it was found that all the synthesized novel compounds except 4F showed very good activity against MMP2. Is the reference? Thank you, sir. Thank you.
Stop sharing, Navneet Gowda. Any questions? If no questions are there, we'll move to the next presentation by Sukanya. Number 4, abstract number 4.
Yes, madam. I'm
Start
present.
sharing your presentation.
Okay, madam.
What your name? Presenter name?
My name is Zirconia SH.
Zirconia SH. Okay. Go ahead, please.
Okay, madam. Can you see the slides, madam?
Yeah, able to see, but you can go for slideshow.
Yes, madam. Okay, my name is Zirconia SH. My presentation, an efficient para-toluene sulfonic acid catalysis synthesis of some new isoxysyl scaffolds and their biological and molecular modeling studies. These are all the contents. Abstract. In this present investigation, we developed an easy and efficient protocol for the synthesis of. In a present investigation, we developed.
Repeat this. Second slide show.
Okay. In the present investigation, we developed an easy and efficient protocol for the synthesis of series of some novel isoxysyl scaffold via para-toluene sulfonic acid catalyzed reaction of 1,3-dimethyl barbituric acid or dimidone, substituted salicylaldehyde and 3-phenyl 5-isoxysol was administered in a reflexive temperature in the presence of aqueous ethanol. All the obtained compounds were evaluated for their pharmacological and molecular docking studies, and the structure were confirmed using analytical and spectroscopic techniques. The result of pharmacological investigation revealed that the compound 4C, 4E, and 4H possesses excellent cytotoxic efficacy, and compounds 4C, 4D, and 4H, 4I have shown better anti-TB efficacy. The structural activity relationship study shows the importance of electron withdrawing group and additional phenyl nucleus, enhancing the biological potency of the compounds. The result of in silico molecular docking studies revealed that the compound C, compound 4H, effectively interacted with P38, MAP kinase, and inhibin alpha enol acyl carrier protein. Introduction. Previous reports reveals that isoxazole is an important heterocyclic nucleus commonly found in various pharmacological active natural products, clinical drugs, and lead compounds. Isoxazole derivatives are paid attention in development of heterocyclic chemistry due to their broad spectrum of biological activity. On the other hand, isoxazole and derivatives are also recognized as important and useful synthons in organic synthesis. Because of the unique pharmacological and computational application, wide effort have been made to develop methodologies for the construction of isoxazole containing compounds. Current chemotherapies suffers a major limitation of side effect and drug resistance. Therefore, constant search for novel and safe anti-cancer and anti-TB drugs remains essential. The current study aims to synthesize novel substituted isoxazole derivatives and evaluate some of their biological properties and binding interaction of synthesized molecules against target enzyme P38, MAP kinase, and inhibin alpha enol acyl proteins. Objectives. In this work, we developed simple and convenient and environmental safe method for the synthesis of substituted isoxazole derivatives via 1,3 component reaction of 1,3-dimethyl barbituric acid or dimidone, substituted salicylaldehyde or 2-hydroxynaphtholaldehyde, and 3-phenyl 5-isoxazole in aqueous ethanol using para-toluene sulfonic acid as a catalyst, and evolution of their anti-cancer, anti-TB, and in silico molecular docking studies. This is the reaction scheme. In that, active methylene compound as a 1,3-dimethyl barbituric acid or dimidone, and this is the substituted salicylaldehyde and 3-phenyl isoxazolone reacted in the presence of para-toluene sulfonic acid in aqueous ethanol refractory 2 to 4 hours. We get a desired product. This is the possible reaction mechanism. In that, active methylene compound undergo tautomerization to form an enol. This enol attacks the carbonyl group of the substituted salicylaldehyde to afford Naviengel product, and this then undergo intramolecular nucleophilic cyclization by the elimination of water molecule to afford intermediate And this finally Michael addition with 3-phenyl 5-oxazolone for a final product. This is the characterization in that the stretching frequency of 3426 is the OH functionality, and 2934 is indicate the NCH3 functionality, and 1676 indicate the stretching frequency of ketonic group, and 1599 indicate the C double bond N group. This is the proton NMR spectrum of the compound 4A. In that 3.30 singlet peak indicate the CH proton, and 3.39 indicate the another CH proton, and 4.95 indicate the singlet of CH proton, and 7 to 8 ppm indicate the aromatic protons, and 12.4 indicate the OH proton. And this is the C13 spectrum of the compound 4A. This is the mass spectrum of the compound 4A. It indicates the 403. And this is the M+ ion peak of the compound. And physical and analytical data of the synthesis compound. 4A to 4E, we used 1,3-dimethyl barbituric acid as an active methylene compound, and 4F to 4-chain, we use the diamidone as the active methylene compound. And aldehyde, 4A indicates the simple salicylaldehyde, and 4B is the 3-methoxysalicylaldehyde, and 4C is the naphthalaldehyde. 4D is a 5-nitro, and 4E is the 5-bromo, and remaining we get melting point in the range 166 to 238 degrees centigrade. And we get more the biological studies in that cytotoxicity. In vitro cytotoxicity was assessed by MKT assay method against MCF breast cancer cell line. In that cytotoxicity result revealed that the compound 4C, 4E, and 4H possesses a significant cytotoxicity with the IC50 value 4.44, 1.34, and 0.15 microgram per ml as compared to other compounds, and standard as an anastrozole and folic acid. Rest of the compounds also display a reliable selectivity, and the compound 4C and 4H exhibited a significant cytotoxicity because of the presence of additional phenyl ring and presence of electron withdrawing bromo group in 4H 4E is the main reason for the superior activity. And the figure 5 shows the percentage of surviving cell of the synthesized compound. In that concentration increases, the cell viability decreases. In that B shows the IC50 value of the compounds. Anti-tubercular activity of the synthesized compound. In that the compound 4H shows the sensitivity at 3.12 microgram per ml. It is similar to the standard drug pyrazinamide, and the remaining compounds are also shows sensitivity in the range 50 to 100. This is the antituberous activity result of synthesis compound. Molecular interaction studies. The compound 4B2I and standard with the P38MAP kinase, and another compound 4C, 4D, 4H, 4I standard with the inhibin alpha enol acyl reductase proteins. In that the compound 4C exhibited least binding energy with minus 10.9 kilocalorie per mole with a 2 hydrogen bond. Is interacted with the amino acid arginine 149 and glycine 170. In that the compound 4H shows least binding energy with minus 11.0 with 3 hydrogen bond with amino acid glycine 96, glycine 40, and isoleucine 95. This is the figure shows molecular interaction of synthesis compounds with the P38MAP kinase and 4C, 4D, 4H, 4I and standard drug with the inhibin alpha enol carrier protein. Conclusion. In summary, we have developed an eco-friendly and concise method for the synthesis of some substituted isoxazole derivatives and screened for the pharmacological and darkening studies. The compound 4C, 4E, 4H possesses and significant cytotoxicity with IC50 value 4.4, 1.3, 0.15 microgram per ml respectively, and the compound 4H exhibited best anti-TB efficacy with minimum inhibitory concentration value 3.12 microgram per ml, and the remaining compounds of C4D4L also shows 12.5 microgram per ml as compared to represented. And structural activity relationship is also indicate the importance of electron withdrawing and additional phenyl nucleus, enhancing the biological potency of the synthesized compound. The result of in silico molecular docking studies reveals that the compound 4C and 4H effectively interacted with P38 MAP kinase and inhibin alpha enol carrier. And these are the references. Thank you. Thank you. Thank you for the opportunity to present. Thank you, madam.
Okay, thank you, Sukanya.
Thank you, madam.
Any questions from the participants? Participants, are they there? The next one, Madhu Gautam. Abstract number 5. Abstract number 5. You stop sharing. Sukanya, you stop sharing. Next, Madhu Gautam. Nada, sir. Okay, Madhu Gautam, then Siraj Sheikh.
Yes, madam.
Abstract number 6, who is that?
Yes. Siraj Sheikh, Dr. Khurshid Ahmed.
Start sharing your presentation.
Okay, ma'am.
Khurshid Ahmed. Who is presenting in this abstract 6? Khurshid Ahmed?
Siraj Sheikh.
Okay, then. Start presenting, start sharing, and then on your video, please.
Okay. Is it visible, madam?
Yes. Yes, please go ahead.
Okay, good afternoon. Myself, Siraj Sheikh, and I am presenting oral presentation. Topic is synthesis, structural characterization, and anti-proliferative activity of pyrimidine curcumin analog. So we are from Abhiday Namdar Senior College. So introduction. The curcumin, which is a phenolic compound, is a constituent of natural ingredient of rhizome, curcumin longan, which is widely used in traditional Eastern medicine. We are uses daily. So it has received great attention over the past of decade, as in it is a antioxidant, anti-inflammatory, anti-cancer, or many purpose we use that curcumin. So curcumin ability to inhibit the growth of various type of cancer cells also, and at various stages of that cancer progression, it is due to the potential to act on multiple target. But the problem is associated with curcumin. It has many promising property, but it has poor bioavailability and weak in pharmacokinetic profile. Therefore, it is not become a good drug. Curcumin is a not drug. The reason for this are poor solubility in aqueous, the gastrointestinal fluid, weak absorption in gastrointestinal tract, and instability at the physiological pH at 7.2 to 8, and the half-life of curcumin is only the 1 to 9 minutes. So the presence of protein increased stability, but after 1 hour, up to about 20% of curcumin is still degenerated in human body. So that is a weak point of that curcumin. So here the many heterocycles which are used in medicine. So we thought that we are coupling that curcumin, or we are making this curcumin heterocyclic backbone. So here we are trying, or we aim to prepare heterocyclic derivative compound containing curcumin framework. So the newly synthesized compound were screened to their in vitro growth inhibition characterization and in vitro anti-proliferative activity against MCF7 by using MTT cell line. So this is a scheme where we build that heterocyclic ring, that is pyrimidine ring, with a curcumin framework. So this blue color indicating curcumin framework with amino pyrimidine. We are preparing this 3A to 3G series of that derivative. So how it is prepared? So it is prepared by general procedure, which is already reported by Luis Pobles et al. So 2-amino-4,6 dimethyl pyrimidine and substituted benzaldehyde were reflux in boiling aqueous solution of sodium hydroxide and in presence of tetra-butyl ammonium hydrogen sulfate, which is act as a phase transfer catalyst, and the reaction was monitored by using TLC, using a solvent system like a chloroform methanol, and the crude product was purified by using chloroform methanol, and it is giving a good yield of the substituted that pyrimidine, that is a 2-amino-4,6 bis distyryl pyrimidine 3A to 3G. So this is spectral analysis of one compound, that is it shows M+1 360. Its molecular mass is a 359, and it is a yellow solid. We get a 71%, and we are characterized by this IR, NMR, and CMR. So this is spectra, IR spectra, NMR spectra, and then CMR and mass spectra. So this is characterized by different spectroscopic techniques. Here, we perform anti-proliferative activity of this synthesized curcumin pyrimidine derivative for their anti-proliferative activity against breast cancer cell line. So here we are representing only MCF7 by using MTT assay with a 5-fluorouracil as a positive control. And this table for that IC50 is given in next slide. So MTT assay, we are performing that MTT assay by this following protocol by using the reference. So cell were cultivated, incubated, and did that MTT assay. So this is some images of this MTT protocol. So this is the first image, which is control 1. So this is a control cell of MCF7. So this is a different concentration of drug, 3D drug we are using here, 1 micromolar, 10 micro, 20, 40, and 80. So you can see here at a control, these cells are live and having good shapes, that is spindle shape and good morphology. But when you added a drug, and if you increase the drug concentration, the morphology is going to change, and that means the cells are going to damage by that drug. So from this MTT absorption, we plot a graph, that is a percentage viability versus the compound concentration, and we'll get this graph, that is a viability is going to decrease as a concentration increases, and from this we plot a graph and find out the IC50 value. So we got this IC50 value for 3A to G and with a comparative curcumin and 5-fluorouracil. So we got this 3D compound which is having this IC50 5.10 micromolar as a active from this series. Then to find out that IC50, so we perform scratch assay or wound healing assay. So wound healing assay, that is the healthy cancerous cells which will grow, and a scratch is given in between them, and this scratch is treated with a cell, that is 3D here for, and photographs were taken is 24 hours and 48 hours. So if here is a cell signaling, then cells are growing and they are migrated toward this scratch and they are joining this scratch. So here you can see this cells before scratch, that is a morphology is a uniform morphology, they are good 100% consolidity, but when it is given a scratch, this is like a scratch. Okay, after 24 hours after treatment of 3D drugs, so this scratch is going to fill by this cell. That means that there is a cell signaling, and there is a 48 hours after that this scratch is fully filled. That means that there is a good cell signaling, and this drug is ineffective to control that cell scratch, means the cells are growing at 48 hours. So here we are comparing this with curcumin of 0.5 micromolar after 24 hours, and this after 48 hours. So in that the cells are migrating, that is cell signaling are very good, and they are migrated to build that patch or that scratch. So if your concentration increases, that gap is remain as or less, it is less signaling at higher concentration. That is the purpose to carry out the scratching. That means the drug at this 8 micromolar is good for controlling the signaling to grow or to reproduce this cancerous cell. Okay, and this is IC50 for curcumin is 10, so below 10 or at 8 micromolar, it is not showing the signaling. So conclusion, so here we have reported a synthesis of pyrimidine curcumin derivative. The newly synthesized compound were screened for their anti-proliferative potential in human cancer cell MCF7 using 5-fluorouracil and curcumin. So some of these newly synthesized product or compounds exhibit good or moderate to good growth of inhibition activity against the MCF7 than the curcumin and 5-fluorouracil. So these are the reference, and we are acknowledged. So we are thankful for DST providing DST phase 0 level for Abid Namdar Senior College, and we are thankful to Dr. P. Namdar, President of our MCA Society, providing that anti-cancer lab to build that anti-cancer lab in our college only. And we are thankful to ICC to giving the platform to present the this work. Okay. Thank you.
Thank you, Siraj. Thank you, Siraj. Any questions? Any questions from the participants? Okay. The next one is E. Harish Kumar. Abstract number 7. Screen sharing.
Madam, yes, madam.
Who's that?
Madam, E. Harish Kumar, madam.
E. Harish Kumar, start sharing your screen and then present, please.
1 minute.
E. Harish Kumar. అంటే నేను వైవ్ నుంచి ఒకసారి మీకు అయిపోతాయి 15 టీ లోపల ఎవరు ఎస్
మేడం నేను ల్యాప్టాప్ లో లాగిన్ అవుతున్నాను ఒక్క నిమిషం
రెడీగా ఉండాలి కదా నెక్స్ట్ 11 ఆల్రెడీ అయిపోయింది సార్ 9 లేదు సార్ 9 లేదు 9 నేహా గోదర్ 5 పంపిన 16 రెడీ ఉంటే చెప్పొచ్చు కానీ 15 వరకు ఇచ్చిన నేను ఆ నంబర్ మిస్ అయింది చూడలే సీరియల్ నంబర్ 15 ఇచ్చేసుకున్నా అంటే 14 అని నేను చెప్తాను ఇది అడిషనల్ ఇచ్చిన మనం 9 ఎస్ హరీష్ కుమార్ మనకి హరీష్ కుమార్ అయితే 1 2 3 బహుశా వీళ్ళు వస్తారు అసలు తెలియదు 4 5 6 ఉంటాయి ఒకటి మళ్ళీ మీదే ఉంది 15 అనిల్ కుమార్ సార్ మీరు చూడండి మరి మీరు ఉంటారు సార్ ఇక్కడ ల్యాప్టాప్ ఉంటుంది కదా లక్ష్మిని చెప్పండి మీరు అయిపోతే క్లోజ్ చేస్తారు కదా అంతే ఏం చేయదు క్లోజ్ లక్ష్మి చెప్తాను 4:30 అంటే వచ్చింది అది మరి ఇది మీది ఇది నాది వచ్చింది సార్ ఈ అబ్బాయి జయంతి జగిత్యాల ఎవరో ఫోన్ చేస్తున్నాను
Mr. Harish Kumar.
Sir, is that my presentation visible?
Yes. You can start.
Okay, sir.
8 minutes presentation. 2 minutes questions.
Sir.
Please proceed.
Yeah, my title of the presentation is an eco-efficient approach for the synthesis of 2-amino 4-phenyl 5,6,7,8 tetrahydronaphthalene 1,3-dicarbonyl via one-part multi-component synthesis use reaction using NaOH catalyst. And here my name is Harish Kumar. I am from JNTU College of Engineering, Jagityala. Here, the introduction, the designing of an efficient, sustainable synthetic methods using simple starting materials and combining environmentally benign reagent conditions is overwhelming existing mission in the synthetic organic chemistry. For this purpose, multi-component domino reactions are considered to be an ideal tool. One part multi-component reaction approaches has attracted significant interest and is emerging synthetic tool to put together complex molecules with a wide range of intricacy. Multi-component functionalized benzene containing 2,6-dicyanoaniline groups are as essential class of compounds in organic natural products, chemistry, material science, and versatile precursors for the asymmetric synthesis. Many methods are available for the synthesis of multi-functionalized benzene, such as catalyzed by DBU, triethylamine, and ethane diamine. However, most of the reported synthetic methods for condensation reaction so far suffers from one or more drawbacks. Many of these procedures demand extended reaction duration, harsh reaction condition, toxic solvents. Furthermore, some of those reactions can be offered moderate yields only. In this view, we have developed a simple, flexible method for the synthesis of multifunctionalized benzenes using simple starting materials in the presence of NaOH as a homogeneous catalyst and ethanol as a solvent. Multi-component cascade reaction of aromatic aldehyde, malonitrile, cyclohexanone with catalytic amount of alkali in ethanol was carried out to give a 2-amino-4-phenyl 5,6-7-8 tetrahydronophthalene 1,3-decarbonyls via novel Michael addition approach. The main feature of these synthetic protocols are moderate to good yield, mild reaction conditions, shorter reaction time, simple extraction of product, and easily accessible catalyst. Its operational simplicity, less need for isolation techniques makes it an additional attractive route for the construction of these title compounds. In the view of the growing environmental concern in the field of chemistry, the proposed
Hello.
Here, this is my experimental. When the benzaldehyde in the solvent of ethanol, malonitrile, and cyclohexanone, and 4 equivalents of NaOH are added to a round bottom flask and magnetically stirred at 70 degrees temperature. And this reaction was managed by the TLC, ethyl acetate and N-hexane 3:7 ratio. After the completion of the reaction, the product were washed with water and recrystallized in ethanol. And this is the plausible mechanism. Initially, the benzaldehyde malonitrile participate in the novel condensation reaction and gives the intermediate one. After that, cyclohexanone participate in the reaction, gives the intermediate 2. After that, the second mole of malonitrile involving in the novel condensation with the carbonyl compound gives the intermediate 3. Further, continuously elimination of the cyanide group and aromatization gives the final product. And this is the optimization reaction conditions in that NaOH using 4 equivalent at 70 degrees centigrade magnetically stirred at 6 hours gives the maximum yield. And here we have successfully synthesized 2-aminophenyl 5,6-7-8 tetrahydronophthalene 1,3-decarbonyls derivatives. And I am thankful to JNTU College of Engineering Jagityala for financial and funding and support. My sincere gratitude to my supervisor, Dr. B. Satyanarayana sir, and I am thankful to Dr. Ramakant Pagadala for his technical support and friends and family. And I thank you for the giving opportunity, ICC and Satavahana University. Thank you, Leelavati ma'am. Thank you.
Mr. Harish Kumar.
Sir.
How you have characterized the final products?
Sir, I characterized by IR, NMO, C13, sir. C13, IR, and
the final products are known or unknown?
Sir, these are known, sir.
Known.
Yes, sir.
What about methodology used?
Sir, multi-component one-part synthesis, sir.
That is known or unknown?
Sir, in that multi-component one-part synthesis, NaOH and methanol, NaOH in ethanol is unknown, sir. It is a new one, sir.
Okay, okay. Any questions from participants?
200 grams by 4,500.
Sir, it's audible, sir.
Is it Arun Kumar? Hello? Arun Kumar.
So, Priya Rani is ready to presentation, sir.
What is the number?
Sir, 0012, sir.
Okay, Priya Rani.
Yes, sir.
Okay, you start.
Myself, Seema Kothari, I am also ready for presentation.
Okay. Priya Rani, you start.
Yes, sir. Yes, sir. Sir, am I visible, sir?
Yes, you can proceed.
Sir, good afternoon, sir. I am Priya Rani RS, research scholar in Department of Chemistry, Coimbatore University, working under the guidance of Satavahana Venkatesh,
Please
sir.
put your presentation in presentation mode.
Presentation. Share.
Presentation mode. You have shared screen, but put it in presentation mode.
Yes, sir. One minute, sir. Share.
Put it in slideshow.
Yes, sir. 1 minute.
Press F5. F5.
Yes, sir. Can you see now, sir?
It is same.
Okay, sir. So, good evening, sir. I am Priya Rani RS, working as research scholar under the guidance of Satavahana Venkatesh, sir, Department of Chemistry, Coimbatore University. And my presentation topic is synthesis of some new non-pyrazole derivatives and the computational studies. And in the present investigation, we have designed some pyrazole and pyrazolene derivatives and all the compound characterized by using IR, NMR, and mass spectroscopy, and also the synthesis component related to DFT and Hawking studies, and chemical parameters such as the chemical potential, electrophilicity, nucleophilicity, and hardness are also calculated by using DFT. And moreover, and we have also done the Hawking studies for the synthesized compound. From the result, we can show that the compound 3B exhibit the more binding energy of all the synthesized compound. In future, these compounds can also be used as antibiotics. Introduction. Introduction. Chalcones are the highly reactive compounds because of the presence of a carbonyl group and presence of double bond. In the present work, we had done the reaction of carbon with that of the hydrogen nitride, which resulted in the formation of pyrazole compounds. And many pyrazole are used in clinical use, such as siloxane, lanaxole, and rimonabant. Also, the quinetazone are the some clinically used drugs containing pyrazole derivative. And we had done the computational chemistry is one of the method of theoretic chemistry used to calculate structure and the properties such as the charge density, distribution, vibration frequency, dipole moments, and also to find the reactivity of the molecules. And computational studies support the experimental results such as the chemical potential, hardness, nucleophilicity, electrophilicity, and energy gap, and the process its application in electronics such as semiconductors, and optimized geometry such as used to determine the bond length, bond angle, and dihedral angle. And we also done the molecular potential. Molecular potential used to determine the electron density of the molecule, and to find the electrophilic and nucleophilic behavior of the molecule. And molecular ducking studies is also used to define the drug designing, used for the drug designing of the synthesized molecule, and also then the comparing the biologically active compound with the theoretically predicted docking studies. And the scheme one, we had done the synthesis of pyrazole and pyrazolene derivative by using the chalcones, presence of hydrogen iodide using ethanol as solvent, and we had done the 3 derivative using such as a HOCH3 and Cl derivative. And these structures are characterized by using the HNMR mass and IR studies. IR studies indicate the presence of an NH group at 3,490, and the 1,200 region indicate the presence of OCO3 group, and the 605 indicate the presence of CN group. And the next, and the expected mass of the compound is 318, and we have obtained the 318 mass of the synthesized compounds, and the NMR of the compound is obtained. The NH peak of the pyrazole ring is present at the 11.64, and the 10.96 indicate the presence of the CH, which is near to the NH group, and the OCH group indication of presence of OH group indicated at the 3.399 due to they indicate the presence of 3 hydrogen atoms. And the electrostatic we also done for the electrostatic potential for all the synthesized compounds 3A, 3B, 3C, from which the electron density of the compounds can be defined, and the optimized geometry homo-lumo of the compound 3A, and the compound 3B optimized geometry homo-lumo of compound 3B and the compound 3C. And these are the chemical parameters which we have calculated using the DFT studies, such as the chemical potential, hardness, electrophilicity, and nucleophilicity. From the we have also calculated 3 compounds, all the parameters for the 3 compounds, and the compound 3B shows the highest chemical potential and the higher electrophilicity and the lower nucleophilicity, which indicates that the compound 3B is found to be reactive from the DFT studies and we also done the docking studies for the synthesized compound. Compound 3A shows the docking energy of minus 219.25 kilojoule per mole, and compound 3B shows the molecular docking studies docking energy of 239.55 kilojoule per mole, and the compound 3C shows the molecular docking of minus 233.11 kilojoule per mole. In the present docking studies, the compound 3B shows the highest docking energy when compared to all 3 compounds. It is minus 239 kilojoule per mole. So the compound is found, thus the compound 3B containing methoxy derivatives found to have the good binding energy when compared to all 3 compounds. Thus, in the conclusion, we can say that the new compounds, the results of the DFT studies indicate the compound 3B shows the highest chemical potential, lowest nucleophilicity, and highest electrophilicity. Hence, the compound 3B is found to be reactive among the synthesized compounds. And also, docking studies, from docking studies, we can say that the compound 3B is found shows the more negative binding energy protein receptor than all the synthesized compounds. Thus, from the above results, the compound 3B is found to be more reactive among all the synthesized compounds. These are the references. Thank you.
Priyarani.
Yes, sir.
Priyarani.
Yes, sir.
In H1NMR, where you got pyrazolene protons?
Sir. Pyrazolene protons, sir. 1 minute, sir. Yes, sir. It is in the range of 4.46, sir.
Pyrazolene protons.
Yes, sir.
ABX pattern.
Pyrazole, it is NH proton. It is there in a.
No. Pyrazolene carbon.
Sir, it is
CH
CH2 proton is there in a
in
the 4.46, sir.
You purify the compound and take H1NMR again. Okay.
Sir.
You purify the compound and
Yes, sir.
record H1NMR again.
We have purified the compound, sir.
No, you have to purify because that ABX pattern is not observed. Okay.
Sir. Okay, sir.
Okay. Any questions from participants? If there are no questions,
okay, sir.
We'll go with the next presentation. Yes, Kotari. Over 10 available?
Yes, sir.
What's your name?
Seema Kothari, sir.
Please present your
Thank you, sir.
work. Please share your screen. Okay.
Yes, sir.
Yes.
Good afternoon to all. Myself, Dr. Seema Kothari. Today I am presenting on green synthesis and structure elucidation of some benzothiazole derivative as potential antimicrobial agent. Sir, voice is clear?
Clear. You can proceed.
Benzothiazoles are heterocyclic compounds which are weak base and made up from thiazole ring fused with the benzene ring and having two heteroatom nitrogen and sulfur, and they shows various biological activity. These compounds have various application in the field of organic chemistry as well as medicinal chemistry. In the medicinal part, they are used as a anti-tumor, antimicrobial, antifungal, anti-inflammatory, anti-Alzheimer's, anti-helminthes, anti-tubercular, anti-psychometric, antioxidant, anti-diabetic, etc. In the present research work, we focus on the synthesis of benzothiazole derivatives by green synthesis method. These are the various applications of thiozoles in the field of cancer. We synthesize various benzothiazoles derivative by green method and water as a solvent. First, from the starting, we start with 2,4-dimethyl aniline. When 2,4-dimethyl aniline treated with ammonium thiocyanate in HCl at 80 degrees Celsius, it formed 2,4-dimethyl phenyl thiourea, which further on treated with a industrial waste, which is a mixture of sodium bromide and sodium chloride. In the presence of sulfuric acid at 80 degrees Celsius, it formed 2,4-dimethyl benzothiazole amine hydrobromide salt, which are further on treated with hydrazine in water, which is green solvent at 100 degrees Celsius. It forms hydrazine derivative of benzothiazoles. These benzothiazoles, when treated with various reagents, they form various substituted shift base like chloro, nitro, methoxy, bromo, or morpholin, chlorophenyl pentane, dichlorophényl pentane, hydroxy, pyrone derivative. So we synthesize approximate 8 compounds by this method. The physical characterization of these 2,2,1-phenyl ethylidene hydrazinyl benzothiazoles are as follows. These compounds are obtained in the 72 to 96% yield and melting points are as follows. All the synthesized compounds are, their structure was confirmed by their spectral studies like FTIR, NMR, mass analysis. The representative compound 4,6-dimethyl 2,2,1,3-nitrophenyl ethylidene hydrazinyl benzothiazole was found as follows. The FTIR shows C double bond C and C double bond N frequency absorption band at 1629 to 1475 centimeter minus. In NMR spectrum shows 2.29 singlet for CS3 group, 2.34 again singlet for 3H CS3 group, 2.42 singlet 3H CS3 group. These CS3 groups are present in this region. C and 6 aromatic protons are shows multiplate from between the 6.9 to 9.4. C13 NMR shows 13.3 singlet for CS3 carbon, 7.7 singlet against CS3 carbon, 21.0 singlet CS3 carbon, 71.7 singlet for shift base skeleton, 124.2 to 147 multiplate for aromatic protons, 168 singlet carbon between two heteroatom, that is this carbon. And mass spectrum shows parent ion peak at 339 M/Z. And other synthesized compound shows again confirm on the basis of NMR, IR, mass as follows. This is a compound 6B, which is a dichlorophenyl, 6C, which is bromophenyl, D, which is 2-methoxyphenyl, E, which is dimethyl phenylethylidene, F, which is morpholine derivative, G, which is 4-chlorophenyl derivative, F, which is H, which is dichlorophenyl pentane derivative, I, which is 4,6-dimethyl, which is hydroxy methyl pyran derivative. All the synthesized compounds were also screened for their antibacterial and antifungal activity. The synthesized compounds were screened for their antibacterial activity against the standard gram-positive as well as gram-negative bacteria. Gram-negative such as E. coli, Pseudomonas, and gram-positive S. aureus and S. pyrogenous bacteria. And control drugs are used as a gentamicin, ampicillin, and chloramphenicol. Antifungal activity check against albicans, Neisser, Calventus bacteria, and nicotine and grisofulvin was used as a reference drug. The results are found are tabulated in this form. Most of the compounds shows active against E. coli, Pseudomonas, S. aureus, and all the tested bacteria more than control drug. But out of all, the compound 6, out of all the synthesized compound 6, I shows most active against bacterial activity as well as antifungal activity because it is the substituted, it has a nitro derivative, so it is shows more active against, sorry, it is a pyrone derivative. 6I shows most active compound among all these compounds against antibacterial as well as antifungal activity. So this process is useful for commercial level, highly effective, and it save manpower, time, utility, health, and safety of men. It process is a environmental friendly because it use industrial waste, which is critical to dispose. Because industrial waste we use sodium bromide and sodium chloride. This process is green process because their waste generation is avoided, no hazardous chemicals and solvents are used, no genotoxic impurities are formation, time saving because process is short, energy saving, no health and environmental hazard, high yield with high purity in one shot synthesis, cost effective for commercialization, and other more benefits are in this process. All the synthesized compounds are also sent for their anti-cancer activity, but results are coming within short times. Thank you.
Thank you, Sima Kotari. Any questions from participants?
Hello.
Yes.
In this, is there a NH proton in your NMR? Where is the NH proton?
Sima Kotari, please answer.
Sir, please repeat your question.
In NMR, you're showing structure and it's NMR. So where is that NH proton?
NH, this hydrogen proton, sir?
Yes.
Sir, sir, there is some results are missing. It is obtained between around 3.3.
Are there any peak in the spectrum?
Yeah, sir.
How do you know that that peak is due to NH? Okay. Any more questions from participants? Okay, thank you, Sima Kotari, for your nice presentation.
Welcome, sir.
Please stop screen sharing. Now, OO13, DN Singh and N Verma. Anybody is available? OO13, authors are DN Singh and N Verma. Next, OO14, Geetanjali. OO14, Geetanjali.
Yes, sir. Myself, Geetanjali.
Please share your screen.
Pragya. Sir, is it visible?
Yes, you can start.
Yeah. Good afternoon, all. Myself, Geetanjali Pandey, a research scholar from School of Chemical Sciences, Devi Ahilya Vishwavidyalaya, Indore, doing my research work under the supervision of Dr. Ashok Kumar Sharma, sir. Today, the title of my presentation is Chitosan-supported zinc oxide nanoparticles catalyzed one-pot synthesis of azepine analogs. And the contents are azepine derivatives and their applications, biologically potent moieties, preparation of the catalyst, characterization of the catalyst, optimization of the catalyst, our strategy, applicability of the method, reusability of the catalyst, characterization of azepine derivatives, superiority of our strategy, conclusions, and acknowledgement. Azepine derivatives and its applications. Azepines are unsaturated He2 cycles of 7 atoms with nitrogen replacing a carbon at one position. Azepine and its analogs exhibit varied biological activities such as antifungal, antiviral, anti-cancer, anti-exotic, anti-inflammatory, anti-tumor, and antimicrobial activities. Biologically potent moieties. There are numerous drugs such as oxcarbazepine, which is an anticonvulsant and it works by decreasing nerve impulses that causes seizures and pains. Diazepam. It belongs to the group of medicines called benzodiazepines and is used to treat anxiety, muscle pain, and seizures. Imipramine is a tricyclic antidepressant used to treat symptoms of depression. Carbamazepine. It's a medicine used to treat epilepsy. It can also be taken for nerve pain caused by diabetes. Carbamazepine is occasionally used to treat bipolar disorder when other medicines have not worked. Caprolactam. Apart from medicinal uses, caprolactam is primarily used in the manufacture of synthetic fiber, especially nylon 6. So for the synthesis of desired azepine derivative, chitosan-supported zinc oxide nanoparticles is used as catalyst, and the preparation of the catalyst is as follows. Zinc oxide powder 0.1 to 1 gram was dissolved in 100 ml of 1% acetic acid. To this solution, 1 gram of chitosan was added and sonicated for 30 minutes. NaOH, 1 molar drop by drop was added until solution attained pH equals to 10. The solution was heated in water bath at 40 to 80 degrees centigrade for about 3 hours, then filtered and washed with distilled water several times and dried in oven. Now the characterization of the catalyst. After preparation of the catalyst, its characterization is performed by following techniques. This slide shows the characterization of chitosan supported zinc oxide nanoparticles as a catalyst. This is the powder X-ray diffraction graph, which predicts that the material is crystalline or amorphous in nature. In this graph, we observe sharp and intense peak at 31.7 degree, 34.36 degree, 36.2 degree, 59.59 degree, 62.7 degree, 7.90 degree, which indicates that the material is crystalline in nature. FESM is field emission scanning electron microscopy. It elicits about the microstructure image of the material. In this image, it shows nanoparticles in rod form with average length of 60 nanometers and average width of 5 to 15 nanometers. Appearance of prominent peak at 363.06 centimeter inverse ascertain the structural purity of zinc oxide. Energy dispersive X-ray spectroscopy is an analytical technique for the elemental analysis or chemical characterization of the sample. In this image, it shows the weight percentage of oxygen, that is 26.87%, and of zinc element is 13.13%. Optimization of catalyst. To observe the optimization of catalytic activity of chitosan supported zinc oxide nanoparticles, we took amount of our catalyst in different mole percentage, and after the completion of the reaction, it is observed that when 15% mole of zinc oxide nanoparticles is taken, then it completes the reaction in 90 minutes, giving 92% yield after completion of reaction at the end. Our strategy. This slide is about our strategy. Our objective is to design and develop an efficient, facile, and rapid one-pot synthetic route for azepine derivative. In first step, aniline derivative is treated with sodium nitrite, concentrated hydrochloric acid, water, pentene 2,4-dione, that is beta diketone, sodium acetate, and ethanol, maintaining the temperature conditions below 5 degrees centigrade. An orangish yellow precipitate appears, which is of 3-phenyl diazenyl pentene 2,4-dione, which is a diazonium salt. In second step, we treat this 3-phenyl diazenyl pentene 2,4-dianol with ethane 1,2-diamine. In presence of chitosan supported zinc oxide nanoparticles and ethanol, reflux at 4 hours at room temperature, resulting in the formation of 5,7-dimethyl 6-phenyl diazenyl 3,6-dihydro-2H14 diazepine derivative. Applicability of the method. On performing this synthetic with varying reactants, it is observed that with 4-chloroaniline, it has given the highest yield, which proves the efficiency of the product. Also, literature reveals that 7-membered ring system is found to be associated with a number of diversified applications. A number of workers have performed various studies considering azepine as the target moiety. For example, molecular recognition, stereochemical dichotomy, reactivity, and various biological assays. Keeping in view the diversified importance of their heterocyclic nuclei as allowed in literature, an impetus has been aroused to construct some novel azepine derivatives. Reusability of the catalyst. A catalyst is a substance that increases the rate of a chemical reaction by lowering the activation energy without being used up in the reaction. After the reaction occurs, a catalyst returns to its original state, and so catalyst can be used over and over again. One of the way to recover homogeneous catalyst is an extraction of product by organic solvent with low boiling temperature. The aqueous solution can be reused as a catalytic mixture. From the graphical representation, it is very clear that we can use this catalyst up to 5 times without affecting any result. This graph basically shows the reusability of chitosan supported zinc oxide nanoparticles catalyst in synthesis of azepine derivatives. Characterization of synthesized compound. FTIR is a rapid non-destructive method that can detect a X-ray a range of functional groups. X-axis represents infrared spectrum, Y-axis represents absorbance or frequency. And its symmetric stretching vibrations are observed at 3,283 centimeter inverse. NH2 group vibration has 2 NH stretching vibrations, symmetric, that is 3,300 centimeter inverse, asymmetric at 3,700 centimeter inverse. NH2 scissoring band occurs at 1,677 centimeter inverse. NH2 rocking vibration occurs at 1,384 centimeter inverse. NH2 waking vibration occurs at 624 centimeter inverse. one HNMR is used to determine the types and number of hydrogen atoms presenting in molecule. Here there are two peaks at 31.632 and at 26.56 is observed, and two small peaks at 24.5 and 28.5. Sorry. 13 CNMR is used to determine the type and the number of carbon atoms in a molecule. Mass, the last one is of mass. Usually we presented a vertical bar graph in which each bar represents an ion having a specific mass to charge ratio, and length of the bar indicates the relative abundance of the ion. Most intense ion is referred to be as a base peak. Here the base peak is at 470.1623. Superiority of our strategy: use of non-toxic heterogeneous catalyst, reusability of the catalyst up to 5 synthetic cycles, short reaction time, wider applicability of the method, simple workup, good yield. And now the conclusion: a simple and efficient one-pot synthetic route for 6-2-chlorophenyl diazenyl 5,7-dimethyl 3,6 dihydro 2H1,4-diazepine derivatives. The synthetic method is an inexpensive and rapid alternative for generating structurally diverse target compounds. A clean and competent reaction with wider applicability renders this method to be of high utility. My acknowledgement and my thanks to Professor Pratibha Sharma ma'am, School of Chemical Sciences, DAVV Indore, Professor Ashok Sharma sir, School of Chemical Sciences, DAVV Indore, Indian Council of Chemists, and my God and my family members and colleagues. Thank you.
Okay. Any questions from participants? If there are no questions, thank you, Gitanjali, for nice presentation.
Thank you, sir. Thank you, sir.
Okay. Next presentation, 0015. Yes, Anil Kumar.
Sir.
Start sharing screen.
Yeah.
Over 15. Anil Kumar.
Yes, sir. We are sharing.
Okay. What happened? Okay. Ready on. Okay, next. Yes, Anil Kumar.
Yes, sir. Sir, is it visible, sir?
Visible. Visible.
My name is
you put it in slides. Share slides. Slide share. Otherwise, also okay. You start. Anil Kumar, start. Okay.
My name is Anil Kumar, Department of Chemistry, Usmania University. My title is Micro-Assisted Synthesis of Unsubstituted Acridine 1,8-dione Derivatives, Evolution of Antimicrobial Activity. Introduction. Heterocyclic compounds having one or more heteroatoms, and these are the largest and most varied family of organic compounds. Heterocyclic compounds are important and are a large proportion of natural products, pharmaceutical and agrochemicals contains at least one heteroatoms. Many of the heterocyclic molecules are essential to human life and other living systems present on the earth. Example, nucleic acids, vitamins, hormones, and antibiotics. Scheme. 4-hydroxybenzaldehyde reacts with propergy bromide in presence of anhydrous K2CO3 DMF at the room temperature to form propagulated aldehyde. Propagulated aldehyde reacts with aryl azide in presence of copper sulfate, sodium ascorbate to form 1,2,3-triazole aldehyde. 1,2,3-triazole aldehyde reacts with aryl ethylene and dimidone in presence of oxalic acid catalyst to form acridine derivatives. IR spectrum. Keto groups appears at 1631 centimeter inverse, CS touching frequency 2951. H1 NMR spectrum. Selective triazole protons appears at 8.01 and OCH proton appears at 5.5 ppm. In C13 spectrum, keto group, keto carbons appears at 196 ppm and OCH2 peaks appears at 61. In mass spectrum, M+1 peaks appears at 629. Antibacterial activity. In vitro and antibacterial activity against gram-positive strains such as Staphylococcus aureus, Bacillus subtilis, and gram-negative strains such as Escherichia coli and Klebsiella pneumonia. The compounds displayed high antibacterial activity against all the bacterial strains as compared to the standard drug. Antifungal activity. In vitro antifungal activity against Aspergillus niger, Aspergillus flavus, and Furaceum oxyporum. The compounds 7D, 7A, and 7K and 7L demonstrated the highest activity against their pathogenic fungi. Conclusions. In summary, we synthesized a new series of compounds under conventional and micro irradiation approaches. However, in micro irradiation method, reaction were finished in shorter reaction time with extraordinary yield achieved. All the synthesized compounds were evaluated for antibacterial and antifungal activities. Compounds 7B, 7E, and 7H showed excellent inhibitory potency against bacterial and fungal strain compared to the standard drug. The compounds 7C, 7D, and 7A were equipotent with standard drug. Acknowledgement. Thanks to Professor P. Leelavati, Madam, Sectional President Organic Chemistry ICC. Thanks to Department of Chemistry, Usmania University, and CFRD for analytical support, Usmania University. Thanks for CSI for New Delhi for providing fellowship in the form of Senior Research Fellow. Thank you, sir.
Okay, any questions from participants? Participants, any questions? If there are no questions, there are no questions. Thank you, Anil Kumar, for
Thank you,
nice
sir.
presentation.
Thank you, sir.
Next, K. Sadanandam and M.
Yeah,
Sarasija.
sir. Sir, good evening, sir.
Good evening. Anil Kumar, stop sharing. Sadanandam, you start sharing. Okay. You start.
Sir, good evening, sir. I am K. Sadanandam, a research scholar, Satavahana University, Department of Chemistry, Karimnagar, sir. Sir, my topic is synthesis of 1-phenyl, 3,4-phenyl, phenyl, 5,4-prop, 2-ine, 1-iloxy, phenyl, 4,5 dihydro, 1H pyrazoles. Sir, actually, today I am going to discuss about the pyrazoline synthesis or pyrazoline derivative synthesis, which were synthesized in our laboratory, sir. Before going to discuss about this synthesis, let me tell some medicinal activities or medicinal properties of my product. So in this heterocyclic compounds played an important role in medicinal chemistry, and they found in big quantities in biomolecules like vitamins and enzymes. And heterocyclic compounds showed antifungal activity, anti-inflammatory, and antibacterial and anti-cancer activities. And another intermediate compound of my product is chalcone, sir. The chalcone has a prominent role. It plays a prominent role in the biological applications such as antimicrobial, cytotoxic, antiviral, anti-cancer, and food additive. And one more important moiety in my product is pyrazoline. The pyrazolines are nitrogen-containing five-membered ring. Nitrogen-containing five-membered ring, five-membered heterocyclic compounds, and pyrazolines has pyrazoline compounds have numerous prominent activities like anti-inflammatory, analgesic, antioxidants, and antimicrobial, anti-cancer. So many biological activities it's shown. So such type of various biological activities and industrial applications of pyrazoline derivative encouraged us to carry further synthesis of pyrazoline based analogs in our laboratory. So to prepare this type of pyrazoline derivative, we should take some starting materials like 4-hydroxybenzaldehyde, that is a simple moiety here, and the propargylation of 4-hydroxybenzaldehyde I'm taking here. Then it is in DMF in presence of DMF solvent. So the dry DMF we have taken. So in this propargylation, the DMF is dry, and of course the propargylation is taking place. This is a propargylated 4-hydroxybenzaldehyde, and this propargylated 4-hydroxybenzaldehyde again now we are taking this. It is reacting with biphenylethanone, and it can form a chalcone. This is a chalcone, sir. This chalcone it is acting as an intermediate compound in my final product. This is a chalcone, and the chalcone is whenever it is reacting with a phenyl hydrazine in presence of acetic acid, it is a microwave assisted reaction. So in this microwave assisted reaction, so we got the pyrazoline. Hello, sir. Am I audible, sir?
Yes, audible. Continue.
Okay, sir. Yeah. So the pyrazoline derivative is formed with the propargylation at the end. So of course this is my final product, which is not unknown, and of course it is characterized by the NMR spectra. So this is a NMR spectra of the pyrazoline derivative. Here this is a ABX pattern. So we should get three peaks. That is a ABX pattern means here this we have a 3.2 and 3.8 ppm and 5.2 ppm. So these are this is a ABX pattern of my compound, and of course and this is a pyrazole in proton. This is a pyrazole in protons, and of course we got another CH proton. CH proton is there. That CH proton is a triplet that is resonated at 2.5. 2.5. This is a triplet. Actually, this is a triplet. 2.5. It is resonated at 2.5. And OCH2 protons also there. So the OCH2 protons are resonated at 4.5. So the 4.5 is a doublet. Okay, the CH2 protons and as well as CH protons are CH2 protons. These CH2 protons and CH protons they couple to each other, and that gives that is confirmed by the NMR spectra. And conclusion, sir, we synthesized analogs of pyrazole derivatives with more yield in microwave assisted synthesis. And all the analogs are characterized by proton NMR and mass spectrometry. And further, we have to synthesize triazoles with my final product by click reaction. And biological activity of the synthesized compound is in progress. And I thank to my supervisor, Dr. M. Sarasija, and I thank to principal of University Science College and head Department of Chemistry, University Science College, Satavahana University, for providing laboratory and library. I extend my gratitude towards Indian Council of Chemists for giving me this opportunity. And lastly, last but not least, I thank to Professor Ashok sir to encourage me in this aspect. Thank you, sir. Thank you very much.
Any questions from participants? If there are no questions, thank you, Mr. Sadanandam, for nice
thank you,
presentation.
Sir. Thank you, sir.
Anybody is ready to present from organic oral? G. Prabhakar, GVR Sai, Madhukar, Ravi Kumar, Ramesh Damala, are you available? Mr. Madhu, are you available? Arun Kumar Arora, are you available? DN Singh and N Verma, are you available? Y Aparna and T Vishnu, K Sandhya. Mamata, Chaya.
Hello. Yes, sir. Sir, myself Chaya.
Chaya, are you ready?
Yes, sir. May I?
Yes, you can. Please share your.
Yes, sir. Yes, within 2 minutes I will share my screen, sir.
Okay, no problem. No problem. Okay, thank you. What's the number? Okay, thank you.
Sir, my screen is visible, sir.
Yes, visible. You can.
Okay. All the respected high authorities of the conference that is organized by ICC. I am Dr. Chaya D. Badnakhe. and I'm today going to present my presentation regarding my research work. The title of my paper is Conventional Synthesis and Study of Alkyl Substituted 1,3-thiazole and its nanoparticles with special reference to the plant pathogens of some vegetable crops. My session objectives are introduction, problem, experimental discussion, result, effect of the newly synthesized alkyl substituted 1,3-thiazole and its nanoparticles with a special reference to plant pathogens of some vegetable crops. Lastly, the result discussion with references. Heterocyclic chemistry is the most varied, classical, fascinating, and largest division of the organic chemistry. It is of immense importance biologically and industrially. Heterocyclic compounds play a vital role in the biological processes, and they are widespread as the natural products. The heterocyclic compounds, which contain nitrogen and sulfur, they possess enormous significance in the field of medicinal chemistry. Thiazole, it is an important class of the heterocyclic compounds studied by many researchers and are reported to possess the wide spectrum of biological properties such as anti-serotonin, antipsychotic, anti-HIV, antimicrobial, etc. So taking into consideration the importance of this thiazole, we thought to synthesize some new chlorosubstituted 1,3-thiazoles from 1,2-hydroxy-3,5-dichlorophenyl 2-bromo-1,3-nonane-dione by the action of phenylthiourea. The scheme that I have carried out during my synthesis of the compound thiazole, my starting material was parachlorophenol. This parachlorophenol is first subjected to acetylation by acetic anhydride and sodium acetate. The acetate layer that we obtain, it is subjected to distillation, and further it is treated with dry aluminum trichloride up to 120 degrees Celsius. We got 2-hydroxy-4-chloroacetophenone. After that, this acetophenone is subjected to chlorination by using the chlorine in acetic acid reagent. The reaction temperature was maintained up to 20 degrees Celsius and the mixture was poured in ice cold water. Later on, we got this 2-hydroxy-3,5-dichloroacetophenone. It is then treated with the aldehyde, heptanaldehyde, and we got 2-hydroxy-3,5-dichloro-4-hexyl chalcone. This chalcone is then treated with bromine and acetic acid for the bromination. So we recovered 1,2-hydroxy-3,5-dichlorophényl 2,3-dibromo-1-one. It is then further converted to 2,4-dihexyl 6-dichloroflavone. This is flavone. The flavone is then subjected to treatment with hydrochloric acid, and here we got 1,3-nonane-dione again. And this 1,3-nonane-dione is further subjected to bromination by dissolving this compound in ethanol. We got this 1,2-hydroxy-3,5-dichlorophényl 2-bromo-1,3-nonane-dione, which is finally in the last step. It is subjected to treatment with phenylthiourea, and I got my target compound, that thiazole. This is my target compound 5,2-hydroxy-3,5-dichlorophényl 4-heptane-1-one 2-phenylamino-1,3-thiazole. The characterization data of the newly synthesized compound that I have tabulated, it was like this. On the basis of element detection and the melting point, the spectral data for this compound, the UV spectra, this is the recordings of this IR spectra, and this is about the NMR spectra. Now, this actually the synthesis part, it was totally carried out according to the routine techniques. The most important part in my synthesis was about the creation of the nanotechnology. I have selected this topic to prepare the nanoparticles because the nanoparticles show more effect as compared to the traditional particles on the any type of the, when we are going to study any type of the activity. So in my whole research, my concentration was to study the pathogenic effect, antipathogenic effect of my drug or my compound that I have synthesized on some fruity vegetables like karela, gilke, then snake guard, like this. So I have prepared the nanoparticles of this compound by using ultrasonic sonopras PR250 MP. For that, I have dissolved my compound in dioxin in order to prepare its 0.1 normal solution. And this solution was taken into the beaker. The probe of the sonopras was deep into it, and the solution was exposed to the sonometer for 10 minutes. During the time interval of these 10 minutes, the particles of my test compound has been converted into the nanoparticles. The extra solvent, dioxin, was evaporated by the routine conventional heating method. The size of the synthesized test nanoparticles of the test compound was confirmed by X-ray diffraction studies using the benchtop X-ray diffraction miniflex. For this, the thin film of the nanoparticles of the test compound was prepared on the glass slide, and then the glass slide was introduced into the X-ray diffraction instrument. And then the crystal size of the particle of the test compound, means the nanoparticle, it has been detected and calculated by this Debye-Scherer's equation. Actually, at the same time, I have prepared the nanoparticles from some other compounds. So these are the data regarding to a nanoparticle size. Now, my whole concentration was about to study what is the antipathogenic effect, or what is the effect of my compound synthesize myself on the fruity vegetable. Because what happens, some of the pathogens are there, they attack directly at the time of the flowering condition of the fruity vegetables. So I have selected some of the important fruity compounds, and then I have again selected those pathogens which are actually they are means making attack at the time of the fruity conditions when the flower is getting converted into the fruit of the fruity vegetable. To study that, I have carried out the disc diffusion method. The punch disc of 6.25 mm diameter of the Whatman filter paper was prepared, and it was dispensed in the batches of 100 inches in the screw cap bottles. They were sterilized by the routine techniques of microbiology. And then the solution of 0.01 molar dilution of the nanoparticle of the test compound I have prepared in dioxin. These discs, they were soaked, assuming that each disc will contain approximately 0.01 ml of the test solution. The culture media for the development of the pathogen that I have used, it was the composition of the nutrient agar-agar containing peptone, sodium chloride, beef extract, yeast extract, agar-agar, maintaining the pH. Now, the most important part that I have carried out in the Department of Microbiology, the culture media was prepared, was sterilized in the autoclave. After sterilization, it was cooled, and this agar was then poured into the Petri plates. They were then, these Petri plates that are ready, they are inoculated with the corresponding pathogens separately on that particular Petri plates, in the means maintaining all these septic condition precautions. The plates were then dried again for 30 minutes, and further delay the disc soak in the test compound were applied in the adequate spacing 2 centimeter more apart area with the help of the sterilized forceps. The discs were pressed gently to ensure their full contact with the media. At the same time, the control was run using the plain dioxin solvent for the aseptic condition. All the plates were kept in the incubator at 37 degrees Celsius for 24 hours. Soon after the incubation period is over, the degree of sensitivity of the test compound was determined by calculating this zone of inhibition. The zone of inhibition I have tested at that time. This is my target compound in the paper that I'm going to present. It has shown the different types of the pathogens that I have taken for the study. They were Aspergillus niger, Pseudomonas lacrimans, Fusarium oxysporum, and Fusarium solani. My compound, this thiazole, has shown 1.5 mm in zone of inhibition, which indicates that it is weakly active for that particular crop plants. The impact of the newly synthesized chlorosubstituted heterocycles on some vegetable crop pathogens, they were, during my study, I have carried out the experiment in microbiology department. The pictures at that time that I got, they were like this. This is again the diagrams of the Petri plates. Okay, before winding up my presentation, I must express my deep and sincere thanks to ICC, principal of my college, Dr. D.H. Pundkar, my supervisor, my guru, Dr. P.R. Rajput sir. And intensely, I would like to mention sincere thanks for respected Dhakre sir, because he has given me the opportunity for presenting this presentation. Thank you, sir.
Any questions from participants? Any questions from participants? If there are no questions, thank you, Dr. Chaya, for nice presentation and nice work.
Thank you, sir.
Mr. Gautam, are you ready? Mr. Gautam, B. Gautam. 0029. Mr. Gautam, 0029. Anybody is ready for oral presentation? D.N. Singh. Gautam. Neha Tiwari. Anybody is ready? Anybody is ready?
Anybody is ready for?
D.N. Singh, N. Verma, G. Prabhakar, GVR Sai Madhukar, P. Ravikumar, Muhammad Khadir, Ramesh Domala. Are you available? Madhu G. C.H. Prasad Rao, Prakash Ram, Arun Kumar Arora. Are you available? Y. Aparna, T. Vishnu, K. Sandhya, K. Arun Kumari, over 17, Mamata T. Anybody available from over 19? Over 20, Nisha Verma. Over 21, Ratan Prasad Achampeta. Over 22, Papiset T. Venkatesam. Over 23, Ram Kumar Rajalakshmi. Over 24, Munna Ram. Over 25, Manjunatha B. Over 26, Kapil Dhawan. Over 27, G. Sivachalam. Over 28, Neha Tiwari. Anybody is ready to present? Hello?